All right, everybody, we'll go ahead and get started here. I think everybody in class has been here, so they're familiar with where the bathrooms are and things, but please make sure you sign in the back. Whether you're getting parking or not, it doesn't matter. I need you to sign in the back. You don't have to do it right now, just before the day's over. If you have anything else, if you have questions for the building, just let me or Daniel know. The people in chat, online, make sure you click everyone. That way me and Daniel can respond to you. Guillermo is busy teaching, so he won't be monitoring chat. We'll interrupt him if you have a question. Otherwise, you should have your accounts sent to your email if you're doing this remotely. In the password for that is capital HPC 2019. It should open it up. And then in class, you already have sheets. Guillermo will go over everything. We actually have a little bit different server than what you're using last week due to some issues that people were having. But if you continue to have issues, we will help you out. So just raise your hand.
Okay. Welcome, everybody. All of you are familiar now with me. But okay, my name is Guillermo, just in case some people in the audience remotely have not attended the previous workshops. Let's recapitulate what we did during the previous two workshops, just for the people who decided just to attend to this one. On the first workshop, it was about HPC, high performance computing, the clusters, how you create, submit jobs, a little bit of scripting, a little bit of the command line environment, that sort of thing. So that is kind of a prerequisite for the kind of things that we did for the second week, where we concentrated in learning Python in the context of scientific computing. So learning Python for research. This time, this third workshop is about a topic that is quite popular nowadays. It's called machine learning. We will be using today mostly one single tool that is called the scikit-learn. Tomorrow we will be using a couple of different packages specialized in neural networks. This workshop, the lessons for today, are entirely based on notebooks. And I will go again into the process of getting connected to the system, start from the beginning. So the new VM is called like this, you see? HPC, yeah. Is like this.
Yes.
So HTTPS. Let me see if I can. Okay. This is what you get when you connect to this machine. jupyterhub.hpc.wvu.edu. You should have received your username. I have my own here. And you will see something like this, except for one extra folder, a couple of things that you don't have, but this is what you see.
I see. We are not able to get in such server on there.
And me neither.
You are 1 minute. We are fixing things.
I was trying to with clearing cookie something.
I actually just met last week.
So,
It's okay? It's
well,
or you will use the. We can try the old one or just in case.
yeah, you guys.
Okay, let's see. Plan B, just in case.
Exact same thing.
Okay, it's like this. It's kind of a pain. I just need one extra. And training. Try this one. Let's see how it goes. Here.
Didn't usually ask.
Yeah, it's the same thing. So I will be using this one because I'm not sure if I have this. Can you enter into this other virtual machine? It's instead of Jupyter Hub.hpc, it will be training.hpc.wvu.edu. Same thing. It's yes, that one is working. Let's see how it goes with this one. So next, let's open the terminal here. I will try to make this big. Okay. Don't do this. It's just for me to know. Okay. Imagine that you don't have that board. I believe. The first thing that you have to execute is JIT.
Some of us have different options.
Yeah. Yeah, for the old one. Yeah. So I'm telling you what you have to do if you don't have it, or I can tell you what to do if you already have it. If you don't have it, you will have to do something like this. So you don't have the folder. Oh, so we're doing this. And you execute this command. Let me see. Let me put it right on top. This command. And I will execute. Oh, sorry. Oh, git clone. And you should, when you hit enter, you should see lines very similar to those. If you already have it, you just go inside and execute git pull. If you already have that. So two different procedures depending if you have the folder or you don't have a folder. In the first one, you are connecting to GitHub and downloading all the notebooks, all the data, almost all the data that you will need. if you already have the folder, you can execute this just to update the new notebooks and the new data since the last version. So those two ways should give you exactly the same thing. Who is not getting up to this point? One. Okay, that's it. The terminal. Now you have that. If you want to make it bigger, it should be able to do that. And for UK, you don't have to, so you will be the first one, right? Everything here is not balanced. You have so all of you are here. I will give you a couple of seconds to get into this. And in the meantime, I will do something. All of you are working on training, or are you? Or some of you succeed to work on Jupyter Hub. Nobody's working on Jupyter Hub. Nate,
I know what's wrong with that.
Some people is using Jupyter. No, the machine is not.
No, it works. There was something fixed. So
okay.
You can use either one.
So you will be using.
Switch back and forth.
Okay, so I will have to do something here. And so give me a second. There is just one file that is too big for me to put it on GitHub. So I put it on Spruce, and I will bring that file back. Okay. So the next step is just copy one file that regardless on which machine are you working, Jupyter Hub or training, there is just one file that is too big for me to put it on VIA. So I have to copy that manually in a slightly different way. So go to the folder, go to 3 machine learning. This is for the 3rd workshop. And here, when you are here, 2019 data hands-on machine learning, copy the file from the TMP here. So execute this command. I will put this on top. That is a command. It's not super important, but otherwise the system will try to download that file. It's like almost 1 gigabyte and takes a while. Do you have the file in place? Okay, so you should have, when you execute ls, you should be able to see this file around here. That's the confirmation that you did the right thing. We will see a few notebooks here, Jupyter notebooks, and you will see this file. Okay. We are just preparing the environment. We are taking this slow. We don't. So please hold some patience. Feel you. Anybody have not this file in place? Can I move on? Okay, so let's go back here and let's start. Click here. So from here, you click here, you click here. And let's start with this introduction to machine learning. This is our first node. So this is the idea. Machine learning is kind of a buzzword today. There are a lot of things that claim to be, and they are not, other things that exaggerate what those things really are. It's a broad topic. It covers computing, it covers statistics, computer science. It's basically a slightly different kind of algorithms compared to those that we saw last week, those in SciPy or NumPy. So algorithms in those packages are very straightforward descriptions of which are the operations that have to be done in order to get the result. So if you want the inverse of a matrix, you basically follow a set of linear algebra operations, some movements, so rows and columns, and you, at the end of the day, you get matrix that, when multiplied with the original, will return the identity. So the set of steps is well defined, and they will achieve the result. Basically, all those algorithms in SciPy follow that part. So the description is well defined. In machine learning, that is true up to a point. But the focus here is to create algorithms that capture from the data and move that data into the solution without actually explicitly declare which are the steps that you have to do to achieve the result. Some of those algorithms still looks very, very close to what, in a spirit, to the kind of algorithms that we saw, traditional algorithms in computing. So you will capture a little bit the idea when we are moving. Another thing, what this usually could be a very large class, let's say, an entire semester on this. So I have to make some compromise here. I will not dig too deeply into the math. The proofs, theorems, all that stuff, I will skip it. There is some very nice material that I can point you, particular for those who want the mathematics behind the techniques here. There is one set of lectures from a professor in Caltech, which are really good. They go into the mathematics of what we will see here. We will not do that. No. That's why I put it this way, practical. This is a very pragmatic thing. Another thing is a lot of this stuff, a lot of this machinery has been developed to process the kind of data that you see in companies who profit from tracking people or gathering information from people. So who sell people's data, like Facebook, Google, that sort of companies that use people's data as an asset for them. So a lot of those things are guided towards word processing, text, that sort of operations. I will try to focus, even if some of those examples are still the classical examples in this field. I try to move as close as possible to a scientific environment where the data are patients or this trying to figure it out different stars, different signals from space or plants, classification of individuals in biology, chemistry. That's a little bit the focus. So moving a little bit away of that. Next thing, I will not cover everything. So of course, it's a very short thing. I will cover what I think should be the basic background, the basic terminology for all those things. And some advanced chapters I will just mention briefly, and they will be kept as a recipe itself. So let's start. Another thing. Most of this material is like a mix and match from several other notebooks that I found on internet. Basically from three to four sources mainly, trying to describe on each notebook where exactly or where I took the inspiration or the material for each notebook. So in this case, for this one, it's a mixture of this workshops here from Yale, the Digital Humanities Lab. They have a nice workshop and a very introductory kind of high level. So the figures and everything, I took it from there. And some of the practical material, I found it from the notebooks created by the author of this book that I use to guide myself into which are the topics that you should see. Probably in another notebook, I actually have this as a link to where the actual notebooks are. And some of the materials came from a variety of different sources. So don't think that this is by any means my own. This is probably the hardest material that I have prepared. It's much harder than preparing the material from just Python or HPC. So let's start very softly into this. We saw basically everything in this box from the last. By the way, some of those things takes time. So don't worry if that keeps working for a while, especially if too many people start executing those notebooks at the same time. So all those commands should be clear for you now, but in any case, I will recapitulate a little bit them. NumPy is the basic linear algebra package for Python. So this is the foundation of everything in numerical computing in Python. One thing, those are not Python. This is not Python. This is the Jupyter Notebook, the IPython kernel, and Jupyter Notebook that allow me to put figures into the notebook and reload. Well, this is more for development. So what really matters is actually this one. And those matplotlib is the standard, probably de facto for plotting stuff. The basic, so again, the foundation of plotting on Python. Some other packages just extend this functionality. So I will execute this, Shift Enter, to get what I need for all the boxes below. So there are several definitions for machine learning. The definition that I like the most is probably algorithms that try to follow the data rather than prescribe a set of well-defined operations. You can do that. In machine learning, you need basically three components to work. One is you need data. Everything here requires data. The more data, usually the better, but more challenging how you process that data. One thing. Another thing that is that the data has to need some pattern of some kind. But this is kind of obvious because if you are in science, you need patterns. Otherwise, you cannot do science. Science is basically the recognition of the discovery of patterns in nature. And thanks God, the nature offers patterns. Otherwise, you cannot do anything. And another thing, basically the reason for using machine learning is not having the ability or the lack of a well-described mathematical equation that solves the problem. Otherwise, you will use that. If you know how to invert a matrix, you don't want to do a machine learning that start exploring the space until you get the inverse. No, you follow the recipe that gives you the inverse and period. It's much easier. So, so when you don't have, okay. Okay, we'll see. When you don't have that mathematical model explicitly, that, and you have all those other elements, that's where you can start using machine learning. There are several topics. We will basically cover this topic well, classification, and we will describe what it is. We will cover this topic probably, yes, hopefully today, clustering. And this one, I'm not really sure if we will cover today or tomorrow. I am trying to learn how much it takes me to produce this, to offer this material, explain. And we will not talking about this, but just for you to know, those are several of the problems, of the big problems that machine learning tries to attack. So now let's go into a little bit of how you classify or separate, or what I call a taxonomy of machine learning. There are several ways of separate algorithms and to distinct different procedures. All of them at some point fail because you reach a point where a classification problem can also be like a regression problem, and a regression problem can also be recast under certain circumstances as a classification problem. So this is just a classical way of looking at this, how you divide machine learning problems. So let's see the classical understanding. Basically, there are three kinds of machine learning problems. First, supervised learning. Where you have basically two elements. You have some data, and you know the answers for that data. And you hope that you are able to devise solutions that allow you to provide answers for more data that lacks the answers. So it's supervised because you know the answers for part of your data, for the data that you use to create the model. So you are in good luck in this sense. All classification, regression problems are mostly in this data. So you usually have all the data of the patients that got cancer, and all the data from those that never got cancer. So and you can use that in order to create a model that allow you to predict if data from new patient will get cancer or not. So this is probably a very good situation in this. You have input, you have the correct result, and you want to create something that predicts results for new data. There is another case where people just throw you the data. Oh, here's the data. Which are the others? I don't know. So it looks like a hopeless situation, but if you think that the data follows, or the conditions for the machine learning problem still are preserved, there is some pattern on that data. So the question will be, what is the pattern in that data? can you know from that data, even if nobody give you right or wrong answers? What is in there? So unsupervised learning, the prototypical case is cluster. Someone give you some points in a multidimensional space, and someone is telling you, okay, I have this data about different countries, all the data. Can you find some countries that are similar somehow? That economically or from the health perspective, they are similar? I have this data from scans from the brain. So can you separate them? Can you get some idea of some of them that are similar somehow from others that apparently belong to a different set? That is unsupervised learning. And there is this one, the reinforcement learning. That is very popular today. We will probably not touch at all this kind of thing in this, but it's the kind of thing that you want to use, for example, if you want to train a car to drive by itself. So you don't know exactly the recipes, but you know when something is going well, when something is going wrong. So you have the data. You have kind of an idea of what the output should be. And all that you can provide to the system is some kind of reward or a kind of grade function of how things are going. So you can train the system to realize, so to take in consideration that if you are touching the board of the street, or you are crossing the line, the yellow line on the left, you are doing something wrong. So it's harder, but this is another. It's also the kind of algorithms used, for example, to train a system to play a game. You know when the game is, you won the game, and you want to teach the system. Now those are with quotes, or teach. The machines are not learning anything, actually. So or put a grain of salt on those. Those are just expressions. Machines doesn't have any understanding of what they are doing. A set of movements that you execute in the game that give you as a winner. And the system can trace all those backs and try to figure out which are the strategies that the system should follow in order to achieve that result. So that's reinforcement learning. So here I have some examples of what it is. Some cases, classification or regression are the most popular in supervised learning. There is one famous case for people in computer science, and it's this one is the Netflix prize, where when this company gives prize $1 million for getting a system, an algorithm, procedure that could improve the recommendation of movies for a given person based on the data. And so they provide the data, they provide millions of points, and they give all the data, and people follow that. And they were at the end, the idea is at the end they were just two teams working on this problem. One team delivered the result 20 minutes earlier, and just for that they won the prize. So 20 minutes is quite an important amount of time for getting $1 million. So you can see, you can search that down on Wikipedia. You will get the anecdotic elements of that. But the point is, okay, this is classification. Someone give you the data and they give you the right answers, and they expect you to figure it out. If I give you new data, what happens? What should? Another typical example from computer science are those algorithms that give you a score and the ability to get a mortgage or not based on your credit score, on those things. So all your parameters, and they figure it out. If based on that, you are loan work. Which brings me another point. Could be very dangerous. So this is okay for scientists to play with the stars, with atoms. Nobody gets hurt with that thing. But this kind of things could be very dangerous. So we can rephrase this workshop like weapons of mass destruction 101. You can really hurt people with this kind of things, especially when they apply to humans, because people understand correlation as causation. This is a very, very typical error, and they can, those algorithms can perpetuate segregation, discrimination, all sort of awful things when used kind of irresponsibly or nefariously. Okay, let's move on. Again, I'm moving first into the global things. Little by little, we've been moving back into scikit-learn practicity. So the difference between classification and regression is that when you are dealing with classification, you have some categorical data. The numbers from 0 to 9, the digits, or you have a well-defined set of species of a plant, or you have different stars with well-defined behavior, and you can divide those elements in categories, in discrete categories. And regression is mostly what we scientists, at least in my area, usually deal with, are just continuing variables. So, for example, you want to create a machine, an algorithm that is able to predict the energy of a given crystal using just so much of it. So one of my previous work, my papers that I have, was on using a neural network to predict the energies of materials. So in that case, what we have is a machine learning model, machine learning for doing regression, for doing this kind of job. You can use the same thing for classification, for example. If you use the same or similar machinery to identify a good from a bad thermoelectric, different problem, but this time it's a classification problem. So classification and regression. So here we have a very, very small example. We will just follow the idea, don't enter deeply into the what is here, to show what classification is, because that's the first topic that we will enter in. Imagine that you have a collection of digital books. And you have around 50 of them on different broad topics, and you have classified them yourself. So you open the book, you saw what it is, and for a human that is very easy. So you saw, and okay, this one is physics, this one is chemistry, this one is math, this one is biology. So you did that for how many? 200 books. Right. And now you have the problem, okay, what I have to do if I receive, or I download somehow, 1,000 books, and I need to classify them. I need to put them in the folders for physics, mathematics, chemistry, and biology. Well, you can do this. You can think, okay, this is a very naive way of doing it, but imagine that I would like to count the number of times on each book that some keywords appear, because I know the words. So I'm helping the system as much as I can. So words like this, life, if there are too many, probably the books is about biology. Quantum, well, this is a big chunk of the physics will be covered this. Bond, chemical bond, or something like this, eventually will cover this area for chemistry. And words will appear, a lot of theorems or things like that. They are probably math books. So we can count, we can open the book, PDF, and there are commands, for example, in Linux, that allow you to take a PDF and extract all the text out of that into a text file, and you can start counting words, so you can play with that. Same thing for most of those formats, the mobile, or the EPUB, all those formats, they have procedures to extract the text from them. And so we can count those things are feasible. And for a computer, it is not that hard to just count words for them. So we have now 200 instances, and we have basically 4 columns, the number of times that each book, those words appears, right? Very simplistic. So we say that we have 200 instances in our training set, and we have 4 features for each of them. The 4th feature is the number of times that that word appears in that book. So we are asked with it, we have the task to figure it out what we can do with that in order to classify 1,000 more books that we don't know what they are. So this one is a very prototypical example of what a machine learning problem is, in fact. So we can put all those 200 books in a spreadsheet, Excel. We can export them, and that's what we take. By the way, this is a good opportunity to say, okay, there is a difference between machine learning and data mining. They are kind of related, but they are separate concepts, and they are separate domains up to a point. Data mining concerns mostly about the problem of extracting data, especially when that data comes unstructured. So you are reading pages and pages of HTML files, and you try to clean that data out. Reading the prototypical problem that is reading all the works for Shakespeare and trying to figure it out what is in there. Yeah, data extraction is a big chunk of what data mining is about. And machine learning is just the models, the algorithms, to get a structure, to create a structure, to discover the actual errors or the diamonds on the data. So think about data mining like extract is just a collection of the dirt, all the soil, and machine learning is trying to extract the gold or the diamonds from there. So let's see this one. I will simulate this problem that I pose with randomly generated data. So I don't have actually the books, and I don't have time to count the words for them. So I will fake the data. So I will be using scikit-learn. I'm not good. Great. Let me see. Oh.
Scikit-learn. It's not working for me.
It's not working? Let me see. Great. We don't have that in training.
It's to your right
Oh.
there.
Hey,
Bring a new terminal.
this one is done. This one is done.
That's it.
The question is, if I do this,
You can do it.
I install it for everybody?
Yeah. 2D see.
Okay. So this was with Conda, right?
Yeah, don't forget your sudo.
Oh, yeah.
I see. Exactly.
Okay.
Do you need to do that?
This
No, just me. It's because I know for sure that Jupyter has this package. What?
Honestly, the very beginning.
Oh, yeah. I'm not knowing the name. Search. So just give me a second. Okay.
I fixed the timeout issue too.
The what?
I fixed the timeout issue on this side.
Okay. Okay. So we'll get into this one again. Let me see. Okay, now
It's working now without
It's working now.
changing anything.
Yeah, you don't have to change it. It's just me that I have to install that package on that virtual machine because it's on Jupyter Hub, but was not in training. And training it was just for Python, the Python workshop last week. So if we need something, we will install things along the way. So here, okay, so I'm creating some fake data. And I am showing you the first one. So this is really fake, really fake, just to get the idea. So I of course, those numbers should be integer, right? If I'm counting words, and sometimes I try to tweak it a little bit, but as those are random data, sometimes depends, it could get negative values. So I cannot have a negative value for the number of counts in a word in a book. But just keep the idea, those numbers are sort of related to the frequency of a word in a text. So we have 4 words here, or 4 values here. For each instance, so this is one instance, this is one book, and this is one book, and this is another book, and for each of them, we label to which category it belongs. So,
Just curious, why are my numbers identical to yours?
because you are not changing and I'm not changing the seed for the random number generator, So you start from the same as I'm doing. So yeah, that's why the random numbers are always the same random numbers. But basically the idea is that there is not such a thing as a pure random number generator, except if you use some machinery or something that through the hardware provides entropy to the system and feeds the generator. Otherwise, it's just following a recipe and they start from the same value, so they produce exactly the same.
Python always starts with the same signal.
It depends what you're using.
Because
So
MATLAB gets some clock thing and then.
Yeah, you can use the clock, but even that thing is not good enough sometimes.
I know, but
It depends.
If
Yeah,
I run 10 times, it's 10 times.
different, and you can force that. In Python, it depends what exactly you are using. You can force to start from a very specific seed,
Right.
allow the time, or if your operating system and your hardware allow you, you can go into those entropy generators, the hardware, and get seeds out of that, so they don't rely on time or anything that can be reproducible, can be traced. And those things, for some areas of science, at least on physics and statistics, those things are very picky. People do those things for several minutes. They move the mouse. They try to do crazy stuff in order to ensure that the random numbers are good random numbers. Anyway, so here is the point. Three boxes here that I'm showing you. I have a collection of 200. So I'm creating here. Don't worry too much about the commands, what exactly I'm doing. I'm using scikit-learn, yes. But with time, you will get the idea what all those lines will mean. So I will get those 200 samples that they belong to 4 different features. And there are some mathematical elements to declare. And I am starting the random generation from 0. So again, I'm generating exactly the same. So here is the first three books. Those belong to the same category. Those belong to a different category. The categories run from 0 to 3. So, this is one of the first things. In machine learning, usually things are high dimension. And except for those very academic examples, where you have just one dimension here, and you can plot nicely, that's hardly the case. Some people use thousands of features, hundreds of thousands of features. So you have no hope of visualizing it on a screen. Not even doing what I will be doing right now. Basically, what I'm doing is a matrix, 4 times 4, to get a picture of how all those different variables are related. We can do this because this is an academic problem. 4 words trying to capture different books. So you will see something like this. So they are basically counting the appearance of theorem, bond, quantum, and lie in all those cases. So different frequencies should sort of guide me to which kind of book is instance belongs. Okay. So we will see one classifier. This is just one example where we're moving fast. Very, very simple. This is the idea. I should be able to identify to what book belongs to just looking which are the closest books to the specific this point that I have in 4-dimensional space. So I can collect, in this case, for example, 1, 2, or 3 books. So if I select just the nearest book, I will say that I have an instance here. I have a new book here in the question mark. So I ask, okay, this book to which class belongs? Okay. One of the easiest, dirtiest way to do this is say, okay, the nearest book, this one. So this book will be on a star, will be this. Okay. What about if I take 3 books and make a poll on them? So I will be taking this circle, and I will consider this kind of book, this kind of book, and this kind of book. And at that moment, I will say, okay, it seems that this book is this one. It's a triangle. Let's say a chemistry book. Okay, what about if I consider 5? So I can go make a bigger circle and include this one, this one, this one, this one, and this one, and say, okay, in average, this seems to be okay, a chemistry book. Yeah. So you see, this kind of classification is simplistic, should work for some cases, but also is very sensitive to what exactly you are selecting. So in this case, it will start. In this case, with chemistry, let's say this is physics. So in this case, it will be a physics book. In this case, will be a chemistry book. And this case will be a chemistry book. So we will be doing this for one example here. We will say, okay, based on this counting, for example, imagine that we are considering this count. 10 instances of light, or the frequencies for light is 10, for quantum is 10, bond is 10, theorem is 20. This classifier, as it is, will predict that this book is about mathematics. Yeah.
It's like they have to exactly this many or at least that many?
Exactly that many.
Make sure to repeat the questions.
Oh, what?
Repeat your question. When someone asks you a question,
okay. I will answer that question. I will see. Somebody make a quick question in the chat.
We got the questions. That's to say, repeat the questions in the classroom. Don't worry about the chat.
Okay. So, okay, the question is, if this should be, what? At least, or what?
Exactly 10.
Exactly. Well, the idea is to start increasing the radius until up to you reach a certain number of elements, right? So if the radius is too small, it will be 0, right? You start increasing the radius, and you will get 1 point entering this hyperdimensional sphere. So it's a sphere in 4 dimensions, right? So it will include 1. You grow that spheres, and at some point you will include 2. But you need 3, for example. If your nearest neighbor is, you build it for 3, it will 2 is not enough. So it will go a little bit more up till include 3. It will be unlikely, but it's still something the algorithm need to figure out. If for a specific radius, exactly you get 1 more. But the probability of getting that when the high dimension is basically negligible. That you have exactly 2 elements to the same radius, and you want 3, but you jump from 2 to get 4. It's negligible, you get this. But basically, you want to count 3. So you will grow in your radius, your sphere, until you enclose 3, and you compute how many they are on each of each kind. You know the kind, and you will get the solution just for the frequency. Okay. So I am posing this because I am entering into something that is really crude into more advanced stuff. So the key nearest neighbors, you select how many, and I will count and give you the answer based on that. So this is the example here. I have this kind of box. I have this frequency of words, and I execute this, and I say, okay, I got a prediction for that book, and that prediction will be, okay, this book is about mathematics. Because I'm using a key neighbor classifier of 5. So what it's doing is, for a specific this set of values, it will start growing the 4-dimensional sphere until 5 books are inside that sphere. 5 books, it's exactly 5 books. And counting them, it found that, I don't know how many, but at least 3 of them are on mathematics, and it will give me the result. So here, for example, is the function to get that prediction on what it is. Let me see. Here, I am making a selection of all the books that were about chemistry, that I know are for chemistry. And I'm trying to figure it out using this key neighbor classifier, which are the areas on a space. It takes a while. That are covered by that classification. So which are the frequencies of the different words that will give me that classification. Okay. Where is it? Okay, I will have to play with the time because the virtual machine is not as fast as my computer. So here, just to mention, I will just briefly mention this problem. There is a situation with this kind of problems, is that in real life, many times you get outliers. Outliers means instances that are very different from the typical distribution that you have on your side. So imagine why is it so expensive? So imagine a book that doesn't have too many theorems and appears the word quantum quite a lot, but still is a book about mathematics. So this is a typical. It's out of the distribution. Well, so there are procedures, and so here's the thing. I think the selection here is reds are all the books that I know are related to chemistry, and those are the areas, and the algorithm is trying to figure it out, the map with for those two words, quantum and life, that those books about chemistry belongs to. So this is what the key neighbors is doing in this case. But again, the point is that sometimes you have points that are out that you have to take in consideration how to remove them. They bias your ability to make predictions. And that's one thing. Another thing is that for the same set of points, different algorithms, and we will see some of them here today and tomorrow, some of them produce completely different results. So here is this is just a figure. I'm not computing this. It's extremely expensive. So imagine that I have this distribution of points, or this distribution of points. So this distribution is okay. I can see that most of the red dots are on one side, most of the blue dots are on another side. So most of those are different algorithms. Each column here is a different algorithm. They are making that separation that way. But here is a different kind of problem when all the blue dots are in an inner circle, all the red books in a different circle. So you see, different algorithms produce different solutions for that. Sometimes remarkably different. So those, for example, are linear. Okay, for example, those are linear models. They cannot perform well in this kind of problems. So you cannot separate with a line something that is a ring with an inner ring of values. This kind of models will never work well in that situation. And here, okay, again, here you can kind of separate those. So red on one side, blue on one side. So linear models will probably work. And what else we have here? They have neural networks. So they are able to accommodate different circumstances pretty well. Separation with a line, circles, lines. So a variety of different classifiers, how they apply to different problems. And that's why there is not a unique solution. And that's why Scikit-Learn, what offers you is a toolbox. A lot of different options with a lot of different parameters and for you to play with the data. So there is no right or wrong in this thing. It's just something that looks better or works better for the kind of problem that you have at hand. So just to give you that, that idea. And to mention a little bit this, let's see if I can get it here. Okay. This is what I was showing you. How is this? This way. To get a little bit more space. This is a problem that we will not tackle during the workshop. It's kind of advanced. But I will mention what it is and to just put it in context. What is the kind of problem here? So imagine that you have some values here. And just by chance, you have something here, and I think there is another one here. Right. So you have this data here that they are clustered together nicely. Those are clustered together. But those trees are completely outliers. So how you can detect those outliers? There are entire sets of algorithms for outlier detection. This is an active topic of research in this kind of area. What they are doing, for example, this algorithm here is called isolation forest. Yes, isolation forest. What they are doing is trying to make boxes and encapsulate those tiny little dots. And you will see that those get encapsulated faster than those. As they are clustered together, it takes more iterations to get the cluster. So you can see what the algorithm is doing in this nice video. So you see that really early in the process, 3 iterations, 9 iterations, 6 iterations, 7 iterations, very early in the process, you get a box for these elements, but not for those elements, not so often for those elements. So this is an algorithm that,
What's the name of it?
this is called isolation forest. Yeah, and this is just a video. This is just, not actually a video, like a JavaScript animation that I found. It's really nice because it shows the concept without entering the actual machine learning. So we will not talking about this for real this class, this workshop, but just for you to know that this is something that you need to take in consideration. I will pause this. So this solution is a nice idea, actually. It's a cool idea that those can be isolated. They are isolated, so that's the algorithm is just following the idea. They are outliers. What the characteristic of an outlier is isolated. Okay, if it's isolated, we can try to isolate it, and this should be easy. Okay. So here, let's see if I probably can do this really quickly, is applying this isolation forest for randomly generated points and a much simpler situation for it. And yeah, so it's trying to capture a bunch of points here, a bunch of points here, and those complete outliers. And you can repeat these operations with different conditions to see if they are really classified as outlier or they are misclassified as outliers. Okay, this is a problem that we will talk about. I'm not really sure if today or tomorrow, it depends. Dimension reduction. And the prototypical solution for that is a principal component of analysis. This is the idea. Again, data usually in this kind of problems are, the dimensionality of that is huge. So we are not talking about just 4 dimensions. We are talking about hundreds of dimensions. In the sense, for example, in the problem with the books, we cannot be happy just counting just for words. We will probably have a bunch of words. Probably we don't even need to know which words because we, for this problem, I provide the words. I could first try to see with a clustering algorithm which are the words that cluster those 4 sets nicely. So I will get that answer. And after that, I will get a whole set of words that's good for that. So the dimension grows. And that also means that 2 points in a very high dimensional space have most chance of being too far apart. If you just see the equation of distance, the Euclidean distance, just the Euclidean distance, in 1 dimension, okay, the difference. In 2 dimensions, you have to subtract and the squares. In 3 dimensions, same thing. You grow. The larger the dimension, it's more probably to 2 points be too far from each other. That's what is called the curse of dimensionality. I will not talk more about that than just that. Yes?
Just a question maybe. It sounds like you're trying to represent here like some statistical like PCR analysis. Is that?
Yes, this is, yeah, without telling you what it is that. So the solution for that is something like that, is trying to get which are the components that could be mixtures of things that represent the data better. So you can shrink the data, you can tolerate some loss to information, some that is acceptable. You try to minimize that. You try to provide metrics to know how many are good enough. So this is a problem of good enough. And so just to put the context of that, yeah, the curse of dimensionality that is often happens in this. And one of the solutions for that is usually something like this, principal component. So just to illustrate that, we will talk about that with more rigor. Consider this set of points. The figure is really nice to capture the idea visually. And this is just an exploration from the visual into the math, into the practice. You have those points in a space, and you will like to represent them with less dimensions than they currently have. So there are several selections that you can do, right? You can select the points like this when they cross this line, and you see that we are maximizing the variance of the spread of those points. You can select a line like this where all those points get cluttered. Okay, so if you are doing this visually and you want to you want to sacrifice one dimension, that's the point. If you want to sacrifice one dimension, you will probably go into this one and sacrifice the vertical distance instead of doing here when all the points will clutter together and you will lose most of the information of that. So this is a nice illustration of the kind of problems. So we mentioned anomalies, outliers, and we are mentioning, so those are the dangers all around this, and the solutions for them. They are also in machine learning. Okay, so now, just to illustrate a little bit, the other set of the problem is for the unsupervised kind of machine learning problems. It's clustered. You have a bunch of points and you try to classify them. There is a nice algorithm for that, very basic. So you have, for example, this set of points and you make a guess of where is the centroid of them. So you compute the centroid. It happens too fast, but so basically what they are doing is computing the centroid, and then those centroids will move and recompute, and they naturally will get those points. So you see that at some point when the centroid moves into here, this point that used to belong to one cluster get detached, and at some point it becomes attached to a different cluster. So you can try that with different number of, usually in one this kind of problems. You don't know how many clusters they are. You are not supposed to know. So you can get different answers, even during different runs. So what people do is running this several times until you get some stability. Or there are algorithms. There are some more complex procedures to know when to stop and how many clusters should be good. Okay, so here's the thing. This one takes a while. It's basically applying this kind of problem to counting words on text. But keep in mind that this is in the spirit of what you can do, for example, if instead of words will be pieces of DNA or pieces of information inside. So this one is basically downloading a book, or downloading a text with data. This data set that I actually move in order to avoid will. Oh, I'm not really sure if I will. I shouldn't compress that. Yeah, probably will even try to avoid this and uncompress it. Let me see. This is what it's doing. It's trying to check if this book exists. If this text file exists. If not, it will try to retrieve the file. I put this file. So I'm wondering if this will try to retrieve the file, this again, even if I put it there. So instead of that, I will fake this thing. Oh. This is a. I tried this morning. I took like 10 minutes, 15 minutes just to download the file. So I'm trying to avoid that pain.
It was very fast for me.
Yeah, so it's working? So probably it's not. Okay. What I'm doing is just manually unzipping that file. So basically, it will take that and trying to cluster words that are related. So let me see, it takes a while. I will execute this. The file should be there. Okay. And here is the k-means. So it's trying to read all that and get groups of words that are related. And you will see that the solution makes sense. Some of those words are actually have similar meaning. And we never provide that to the system. So words like billion, million, they are kind of related. So you see here, okay, the first one is the stupid one. But you see, for example, those words here are related somehow. All those words are kind of power indications. So the system doesn't understand anything actual at all. But just from frequency, just from how close one word is to another, is basically applying the same idea that we saw here to cluster that. Those words are related to each other. So the distance is no longer a geometrical distance, it's just distance for a text. So you see that those algorithms are very flexible in being able to move from one domain to another. So yeah. I found some interesting material around. Some of them I use it, some of them I never even have time to actually look at it. This one I use in a lot, this book, because I have it and because it gives me a good balance for this delivery presentation. And this book, I forgot. And there is one from a professor in Caltech. So you just say Caltech machine learning, you will immediately know which lessons I'm talking about. Really good, far more mathematical. So it's just to get a good foundation on what all is about, but it's still practical in a sense. He shows the concepts. The concept's really nice. So let's move to the next one. So now this was an overview of the concepts, just the concepts, not much into the scikit-learn. This book, we will apply classification, we will apply different elements for one problem, just one problem, and we will see what the problem guide us into that. So the problem that I select, also this one, again, this material is a mixture. So again, it's of several places. There is one from a machine learning class, University of Turin. So from some Italian people. Some of that also from the from Andrea Aurélien Geron, the book Hands-on Machine Learning. So let's see. I need this. And now we are to start digging into how scikit-learn actually works. For most part, scikit-learn offers classes, objects. So scikit-learn works like this. You create an object with some parameters. So they use a lot of object-oriented programming. So many of different models offer exactly the same functionality for you. And the input for that is usually two elements, at least for classification and regression. Samples, so that are NumPy arrays typically, could be lists, could be pandas data frames. They are able to work with all of that. And in the case of features, it's just in the simplistic case of one-dimensional feature is just the list of answers. So the known answers for the problem. This is how that works. So you provide those two elements, at least for that classification. For a clustering problem, you offer just this because you don't know the answers, so you don't have this. You just have this, and this is what you offer. So the columns with the feature will be the features. The rows will be the instances of your data. That's one. So the feature matrix looks like this. Here you have n instances in your training data. You have d dimensions in the number of features here. And the labels, when this problem is with one output, one single output, one scalar output, if you like, is 111 for each instance, right? So this matrix is n times d. This array is just n elements. We have n samples, d features. This is how that works. Just with this, we will start to dig into this problem. This is a very classical problem in machine learning. So it's easy for me to find the data, get all the examples, and get everything working, and it's really nice to see. So this comes from some data. This is actually, they mention as one of the oldest problems in machine learning, because the data comes from tables or collection of measurements from the 30s. So it's quite old. So they have 150 instances of flowers, measurements of flowers collected in Hawaii. And so they are able to distinguish 3 different classes. And what they did was measuring this. For the sepal, they measure length and width. From the petal, they measure length and width. Sorry. So 4 elements on each, for each instance in the sample. So they have this for the sepal, this for the sepal, and same thing for the petal. 4 features. Clean data, no missing points, everything is, it can be done. And the problem is not that big, so it's really cool to use. And they are able to, the people was able to, okay, this one is from this class, this one is from this class. They have the answer for all those 150 instances. They know what they are. And another thing that is really good for this kind of things is that there are 50 of each. So it can be better. It can be better. In a reasonably good amount of entries. Everything is well separated, 50 of each of them. This has been used in several papers, so I put some of the papers that when this is described. Again, this is a classical problem in machine learning. So there is a Wikipedia page for it. There is some description here in this web page. This guy is using MATLAB for that, and it's in Chinese, while it's in Taiwanese Chinese. So, but they still have some English portion of it. So I couldn't understand. And this is a classical problem in pattern recognition. So it's so classical that scikit-learn even give you the data. It has the data inside, so you don't have to download anything. They have the data for this kind of problem. Again, 4 features, 3 elements here. And this is how you import the data. Did I import the first thing the first time? I don't remember if I did this. Okay. Yeah. So this is how you get that data. By the way, there are several like this in these data sets. We will see how far we go, but if we have to stop in a minute, we give a minute to relax on this. So there are load something functions in scikit-learn where you can get different data sets that are, let's say, classical in this. There is one for diabetes, itis, from handwritten words. There are a variety of them. I probably have the list of them below. So you see the data set is well organized, is well structured. It's something that is usually not the case in real world. No missing data, everything is nice. You have the data, so you get a dictionary. When you get the object, you get a dictionary. This is the data. So this is the known answers. So this is the classification for them. They know what they are for those 150. And they have the names for them. So the names are those iris setosa, versicolor, virginica. They have a description, that is what I'm showing you here. So nice description, each what they are, what they hold. And so everything is here. So you can read where they capture. Yeah, 36. So this data is from this year. Actually, it's quite old. So you see here, we have those features. Those are the names. So those are the names of the columns that we are getting. 4 columns. And for each of them, there is a classification. And the classification is just with 4 digits from 0 to 3, but they actually means this. No, 0 to 2. And they actually mean 0, 1, 2. So you see here, the matrix, as a NumPy array, when you get this, is 150 rows, 4 columns. You see here that this is actually a NumPy array, the shape of that matrix, so it should be fine. Those are the first elements in the array, just to get an idea of the data. So measurements here, length, width, length, and the target. As I told you, zeros, ones, and 50 of each. So here, I cannot observe all of them, of the 4 dimension again. What I can do is select 2 to see this picture big. So here I'm selecting feature number, the 3rd feature and the 4th feature. So all the features related to pedal, right? And I'm getting a picture of that. First thing that you see, okay, this one is easy. This one is probably not so easy, right? And that's typically what you will see below for all those elements. That Virginica and Versicolor are kind of mixed, and Setosa is well separated from the set. What I did here is same thing this time. 4 rows, 4 columns, mixing all the same with a grid of plots, just to get a picture. So you see, I can select 2 of them. Again, nice separation between this one, but here is mixed. So here is a mess for this. It's separated, a mess. This one is not that bad. You can imagine that probably a line around here separate those things. This one again, a line with some misses here. Here, so Setosa is not a big deal, but those 2 are kind of problematic. So I will be using one classical solution for this kind of problem that is called a logistic regression. First things to know, okay, actually, before I enter into this, I will just mention this and we will give a few minutes to relax. I need that. Logistic regression is not a regression thing. It's a classifier. The name is regression, but it's not a regression. So let's take 5 minutes, relax a little bit, stretch, and we will work on how a classifier, the logistic regression, can attack this problem. That's it. Okay.
Everybody make sure they don't forget to sign in. You park and get it. It's like 30 minutes. Good morning.
Who of you are familiar with machine learning somehow? Okay.
I did an MG course and for Coursera.
You took that? So I'm going too slow, or I'm going the right pace. What do you think? It's too slow. I can, like those videos where you should be looking at this at 1.25 to get it the right speed. 1.5. Should I go faster? Should I go slower? What do you think? Who thinks that I should go faster? And what? Okay.
Who thinks you go slower?
Who thinks I should go slower?
Who thinks you go the right speed? Okay.
Do we have an exercise or something like that? Because
Yeah.
as you said, it's very hard to follow, so we need to do something.
Yeah, you need to do something. So what I would propose to do is again, first was very generic, not the global thing. So this one we will tackle one problem. We will give you some time for you to explore a few of the data sets to exactly like this. Exactly like this. Here. So you can start looking at that. Open a new book and a new notebook and start looking at some of that. Load something. There are several. And I don't remember if I have it here or not. So let me see if I can get it. So here. You see all of them. So the first part will be familiarizing with the data. And one way is to start getting those that are free to get. So the Boston house pricing, I think it is, breast cancer, diabetes, digits. So this one, wine. So those are classical problems. They don't have too many, the data is clean, no missing values, as far as I know. No duplicates, so everything is clean. So no data mining to do here. And they don't have too many dimensions, so you can start playing with them. So this is one. So one thing. Another thing that they will see, we will see this in the moment. There are fetch functions. So they are load and fetch functions. Load is that they have the data is so small that they have it. They have the data. They have this one where the data is not inside scikit-learn, but they have the functions and they know where to take the data and how to download the data and create a nice data set out of that. So for bigger data set. In particular, I will be doing this for one, and I will show you from this side. You can go here, OpenML. It's a repository of data sets, and they have connection with scikit-learn, so you can basically search, for example, let me see. If I search for this one, I would probably get there. This one. This one is one classical problem. So they have many, and all that you need is the name. And if they have several versions, they probably give you which version do you want actually. This probably has just one version. So there is a function that allows you to recover the data set from this database, of data sets. So with this fetch and this OpenML, for example, right? OpenML. And there is a kind of similar to the Boston. The Boston is the classical problem in this. There is one for the entire California house pricing from a few years ago. So from a few years ago, the houses still cost like 3,000. So it was quite a while. They don't cost that any longer. So they have those data sets there. And the next step, so this is the first step is load, small data sets with load something, fetch. And if you want to go for real, there are two places for getting data. This, let me see, is cargo, what is it? Display. They have quite a few. You have to probably you have to register free to get access to this data. They usually in CSV files, JSON files. I download a few. For example, I download the gas prices in Brazil, so you can have a look at that. They are not so clean. So sometimes I have captured instances that I duplicated. In those data sets, missing values, so a little bit dirty, but still it's something to play with. And there is another one that is escaping me right now. When I got to my mind on them, I would say. So those is just you download the files and you build the data out of that. So let's continue. Okay. Where we are. Data here. Logistic regression. Again, regression. This is the name, but this is not about regression. It's a classifier. So we will get it in the data here. Just two elements. So just, and we are classifying this. This is we will work on this as a binary classifier. So we have 4 instances, and we will simplify the problem into determine if something is Virginica or not Virginica. So a simplified problem. So I got this. And basically here I'm creating this object. This is how it works. You first create the object, this is the object. From this class, as a classifier, you provide some extra arguments, some fixed numbers in order to reproduce this with the same numbers again. This algorithm is for a local minimization, so how to find the minimized one. And now I am providing the data. Two elements of data. This is a classifier, so this is supervised learning. So I have to provide two elements, the data and the answers. This portion, this execution is what takes most of the time. It's so small that you see nothing, but this is what you actually are doing some computation. You are not doing any computation when you create this object. No, you're just preparing the machine. You are getting a machine with some predefined values, some predefined nature, and you are actually doing something here with the fit. And you get nothing out of that. Let's say you will see nothing, or you will see something like this. Okay, this is a logistic regression, and you have this parameter that you never mention what it is, so the default value is 1. And there are some for the solver, for the local minimizer. So there are some tolerance here. Again, you never mention about that, so it's the default. And you get this. So you get the machine here for you. But this machine already execute the feed. So they are able to do predictions at this point. The predictions do, in this case, getting the probabilities. So it's one thing is, for at least for the logistic regression, is one thing is telling me if something is, what is the two sets? Virginica or not. Another thing is what is the probability for that I got for this instance being Virginica or not. So this is a special function just for the logistic regression. You get a probability. In some others, you are not able to get this. So it's basically telling you, okay, for those are the lines that differentiate those two classes. And remember that I am providing just this here, and I'm providing just one.
Does that mean that's a third variable, or what?
Yes, let's have a look at this. Okay, I think it's good. When we create, I actually never did it, so I should be doing this. This is what I should do. After I get this, I am getting just one value. The whole data set contains 4 features, but I'm capturing just one. What? This one. So if you want to see this, it looks like this. An array, and for each instance, I have just 1 byte. I restrict the whole data set just to get one. And again, I also make a restriction on y. So y.shape is just 150 instances. But the answer for that is a bunch of zeros for all those that are non-Virginica, and a bunch of ones. So 100 elements here. There are 100 elements here. 50 elements here that are Virginica. So I oversimplify the problem. I am just looking at one feature and trying to figure out one feature. And I have just one question that is with a binary answer. Yes or no. Is or is not. from that class. So this is telling me, okay, when I cross this threshold, I am moving into one region or I'm moving into the other region. So let's see what I'm doing here. I have a few instances on how they move into non-Virginica, non-Iris Virginica, those here in this line. So they are moving into this direction, and those are moving into this direction. And I have a boundary here where I'm moving to one or another, and I'm classifying those. And as those are mixed, I always make a mistake. I always have misclassified elements, always. Because if I move to this direction, those points here will be classified as Virginica, not Beam, in order to classify this correctly. So I will classify this correctly, and I will penalizing all of them here, all of those, if I move my threshold in this direction. If I do the opposite, if I move my threshold in this direction, I will classify this correctly, but I will misclassify some of them, right? And we will see how that translates when we see. And this is actually interesting because we have an imbalance here, right? We have 50 of this and 100 of this, right? But we will see that in a far more extreme version of this later, when we talk about precision, accuracy, all this stuff. Okay. So the boundary was 1.6. 1.6. Oh, well, I never actually. 1.6. Let's have a look at this from here, I think. Let's see. I'm looking at better way. So here, what I get in this? I am just looking at this to classify things that are either here in yellow, I think, or those here. Those are easy, but those get in touch. There are elements in one side, so just this one single variable will not be enough. That's why it was chosen that way. We'll see. Okay. And here's the prediction for a couple of elements, for a couple of values. So again, if the value is small, it will go into the non-Virginica. The value is high, go into Virginica. The value is small, below the threshold, it will not be. So you see that those two values correlate with this decision of having a boundary, right? 1.5, 1.7. So what we were doing here is having the same thing, but this time we have two features instead of one. So we are adding this column and this column, and things will improve a little bit. We have more data, so we have some separability here and some separability here. So we will see how good it is. When I'm doing this here, and also I'm getting these lines. So I am getting here one of the features, another feature, and determining how I can separate those two instances with a line. This is a line with a logistic relation. we will see this with another technique that is called support vector machines. The idea is similar. Create a separation. Okay, here. So here I am moving a little bit more. I am offering the whole tree distinction, the 3 different flowers, but still keeping just 2 features. And now this logistic regression will give me a separation between this, for those 2 features, which is the separation to those Virginica, the versicolor, and the setosa, right? Those are lines here separating the regions. So we are moving little by little, making more complex the data set, offering more. So same thing here, 2 elements trying to separate the areas. So we use this an entire procedure for getting a classification. We can move this. The next step, the final step, is to move beyond just 2 features. That will be the next thing. Okay, but I will stop here. I will mention classification as a whole new notebook for classification. And I will skip the logistic regression because we already showed a little bit what it is. But we'll see this in a more general context. So I show you this. And this is, we moved for a few minutes for exercises, so you explore a little bit. Choose your data set and start looking at it and try to get something, try to mimic this. Try to at least get an image like this. For one data set that you choose in the collection. Some of them have more than 4 features, so you have to restrict your data set, so you play with that. So this is your first real exposure to scikit-learn. So it will be simple, but please do it. We'll give you 20 minutes for doing that. So choose one of those, for example. Those are very simple. Choose one, see how many features, how many they have for each of them. If you are happy with that, if you want to restrict, see how those things were restricted here. So here are the tricks for restricting dimensions. So really easy. If you want to explore later this fetching of data sets, I recommend use this one. This one is the only one that I actually use for, and this one contains probably all of them directly. The only thing is that you need a more recent version of scikit-learn to have this function. Other than that, it's okay. And there are also those that are just numerical data sets. That I use this for the blobs to create chunks of points in a space that they follow some distributions or space. So just for playing, if you are more interested in just get the numerics and you don't care about, so if you are more in the mathematician spirit, so you don't want to see the real world, you just want to see numbers popping out and get the ideas out of that. So probably those are the make functions, give you the numbers. You don't worry about real life. Again, to complete the picture here, how scikit-learn works for most part is with estimator objects. And the logistic regression was a classical example of that. So this is how you get access to an estimator, linear regression. Linear, this is in sets. So we'll see that. I have a map where you can see where they belong. This is in the linear model section. Linear regression is one of them. Logistic is another. And they have parameters that you can tune when you build the machine. And this is when you see the object, you basically get access to or can see all the different parameters in that and the defaults. If you execute something like this, I never did it here, but you can also do this. Let me see here. It's because I never executed. This way, in a notebook, in a Jupyter notebook, you get all the different parameters and what they mean. So this is, again, this is building the model, this is building the machine. No computation, this is super fast. Or you do it another way, is with the help and you get the data inside. So basically the same thing. All the different parameters, what they mean, are there. Okay, and when you print that, or just simply like this, in the case of a Jupyter notebook, okay, I never execute this. You will see all the parameters. This is the first step. You create a model. Next step is you feed the data. And third step is you predict data out from that feed. This is how those things work. There are more things, of course. You can cross-validate, you can do some other stuff now, later, or extracting probabilities as we did for the logistic regression. So here is one example before we move. Let me see. Okay, and this is I duplicate that. So I will finish this and I will give you some time for the exercise. So the numbers, bunch of numbers, just to play with the linear regression. So I have this points. I randomize a little bit here. So I have the points up and down a little bit. And I am here, I am feeding the model. This is so simple that I just get the coefficients, so the weights, in this case the slope, and the intercept. And this one should be close to 0.9, because this is the slope on this fake data. So I just randomize a little bit, but not much. So the value that I get is close, should be relatively close to this one. And of course, the intercept should be 0. I'm not getting exactly 0 because I'm randomizing. So the linear regression is doing the best that it can with that graph. So, but this is how this works. So please have a look, choose one data, choose one data set, start exploring. If you got stuck in that, call me. What I would like you to do is select one data set, start exploring, get something like this. So some picture of the data, because the data is so small that allow you to do that. And if you want, try something like this. Try a logistic regression. Try just select 2 values. Do a logistic regression. If you feel uncomfortable with the logistic regression, do something even simpler first. That will be the linear regression. This is much simpler, like this, the linear regression. So right now we have seen a couple. This is actually a regression. The other was a classifier. So we are, don't get confused with the word logistic regression. Logistic regression is a classifier if you want to use a problem about that. If you are not sure this one is, the diabetes is okay, the number is not that big. But take your time. Take your time. I will give you 15 minutes, 20 minutes. The diabetes is not that bad. They have 10 features. I was looking at breast cancer is a little bit bigger, 30. Again, you can reduce, so let's see. What is this?
Excuse me.
Sure.
So I don't know if I can do so what I'm trying to do is others. I'm like doing it with technical.
So which one you
So so I got the data description.
Okay. So how is all do that? This is your option. Okay, so the right. And so you know the keys. So the keys. The keys for the data set. So here's the data. It is dictionary. Here is where you saw the description. So you saw the description. They have 440 instances. They have 10 columns.
Yeah.
And this one.
So this target is not like quality.
This is this is the answer. This is the answer. The target.
So like the target because it's just a target. I want to this
When you want to classify.
call this.
Yes. No, it's just there is well, it is sure well, usually some problems are they don't have targets. It's just the data. So they are used for only for clustering. This one has target. So targets are not. Let me see what they are. If they are, for example, probably this is it looks like probably more for migration. It's a nice one.
Oh.
One.
So it's like
Let's see what they are.
there's some store
Yeah.
later, so it's not like it's a no, but it's a no for submitting this.
Yeah, these are real numbers. Right? It's not what we yeah, it's not score. So it's not something it's like the ideas that is just three different species. This is a problem for regression. It's not a problem for classification. So that's one thing. Some others they don't have any targets, so those are problem for clusters. Because you don't have the answer, you don't have the answer. You for this you have the answer. The answer is something that follows like a real number, something that you can calculate the value, and you can figure it out how to predict this number from this 10 figure. Right? So sometimes this dot notation works. and it's working here, and I'm trying to check what is not working, right? So this is exactly the same to do this, right? Exactly. It should be, you should be able to get this and actually it's working. The question is what the target something. No, not target. Yeah, for some reason this name is not it. This is probably no, my name is not. But this is probably bug. As I said, it's not working with the dot operator. But it's not the diabetes. Yeah, so it's for this data set that this is not supposed to be target.
So what are the dictionary keys that we have? We have that.
We have that.
Wow.
That's all you're plugging on.
I'm doing the same one as you.
You asked it. Oh,
Oh yeah, they don't have
I
they don't have it. So it's not. But
there's two
it
ways.
would be for some other kind of
Small steps. There's it depends on what comes before.
Yes. So this is what diabetes
MAR.
MAW. That was it. So some data and here, some target.
I'm not.
That means the progression or something. And the description. You see actually when you're doing. That the file name, you don't care about the file. The target file, you don't care about. And so yeah, so you get real information. This.
I think I'm
this. So what kind of things you can do?
We have
What
5
kind
and
of
6 things.
equations you can pose?
5 and 6.
Thing is, for example, for those 10 columns, you can manage that cluster. So there are different individuals. There are similar somehow. Some collection of features. You can see this.
That needs to be lost.
440 observations, 10 columns. Right, it's 400 rows, 10 columns. Right, and you have yeah. One.
That's it. We're working. Just add a folder.
Oh
Holy crap.
So, let me see. That. So let me see. Let's see all the page. I would like just to see the image. Should be there. What do you think? Because I got let me see.
Where you at?
First.
Try to figure out what's going on. Let's just grab some of this. Figure out
What I might
that's why I wouldn't know. That makes sense. The stuff
Oh, there is.
Yeah, see this, and this number. That's what I can only.
The house requires an investor.
They
The house
data
requires
and they normalize, they center, scale, standard. So that, so you got, yeah, so that we don't have access to the actual age, and you cannot revert. It's just for playing with the data. Because yeah, that's a
I
clear.
like how they sex. Just like,
Let's
set
see.
it to zero.
Yeah. Let's see. Probably will only normalize that. You put minus 0.5. They should be categorical.
This is so.
No, sorry. All the data. Number one. So, you see that are basically two numbers. So this is yes. Yeah. This is still really black and white gender orientation. So there is not a new spectrum anything in between. Nobody is getting gender zero. So yeah. This is really black and white. It's just a normalization. I don't understand why it's not. Maybe why it's not. Maybe it's the
I think they have
Yeah, we
zero.
don't have any class on this.
but how do you get? Let's say first new sentence. So you want new sentence 0 and once new sentence you get minus 0.5. 0.5. But after they change the standard deviations to be so the scale, the centering I understand. The scaling such a way that the standard deviation times n sample is on the square. So that's where
Yeah, you can imagine because they don't have the same number in their email, so they have to figure out
they unbalance.
they
The balance that they have.
the center is
Exactly.
zero,
Yes.
it's something.
It's not like the other that is 50-50 and 50. There is
Yeah,
a
that's
Yeah. So you can still play with the regress by that or you can so it's your X.
Oh, okay, so it doesn't matter.
the wine.
That's what your X is.
Plastics.
So that is a good. This is a more regression problem. You can convert it into a classification problem, for example. Kind of dirty, but you can decide a threshold for the value there. And you can say, okay, the values that are, you can do something like this. And what is that in the target first?
No.
Target. So target are those numbers. So you can ask, okay, which are the values for target? Okay, first, what is the maximum? Max. Okay, 25, 100. So, yeah, so we can say, okay, which target is bigger than 200, and we get 2 of those. So yeah, so you have a threshold, and you say, okay, I will decide this, and with this, we're using this instead of that, it will be common classification. Yeah, so you why would you call this case? And something else. One.
Zeros of that. Facts.
This is zero. Okay, there is another.
Actually, that's. Hey, look, crime is higher the closer you are to the city. Oh, I learned today. I'm too scared of you.
Yeah. What? Well, 0, 1, 2, 3, 4, 5, 6. Hasta.
Oh, so okay.
So yeah,
Sure.
house.
If that person.
This is the second.
So the larger we.
First to decide the threshold, and now we record the application classification.
Let me do it again there.
I would call it. Let's say. Oh. So instead of using the number, I was using the and now we can use logistic integration and the whole. As a classification. Yeah.
So after that,
the dark part of this thing is that this 200 was complete traffic. But we decided 200 out of none.
challenge
It's
is
super rapid. All yeah. But this is just for the sake of like, we should keep this that we did something to but yeah, we recast. Okay, so let's continue a moment here. Just to complete this notebook, with the same iris, with a much simpler classifier, will be using exactly as I did before for the books. That we decide, okay, with a circle, this should belong to this one or this one. You will see the danger of that in the field. So I will recreate again the Irish that I said,
I thought that was like
and I will create this.
See you later.
Okay. So this time we have this estimator. For this estimator, we have arguments like this. In this case, how many neighbors? To classify how many neighbors should I use? And I'm telling you, okay, use just one. The first one, the closest element to any point that I give you, it will be that. I'm trying to predict one element here, and it will answer, okay, this is region. However, as you will see here, this comes with a danger. Same as the book. And a small change in your classifier and your answer will be totally different. So we have classified the area, at least for those two features, this way. It's just the closest. I'm basically mapping the area. In Virginica, Setosa, and Berkeley here, this way. You change this here, I can go back here and change into 5, and you get a different picture. Completely different picture. Try to change 1, 3, 5. The picture is completely different. Why? Because we have features that are overlapping each other, at least for this count. And same exercise with something that we will see by the end of the day, maybe tomorrow. Support vector machines. In this case, support vector classifier. Here is the estimator. Again, see that the pattern here. This is an estimator. Those are the arguments for that estimator. This one just needs something called gamma. We will see that later. And here is where we are actually doing operations, the fitting, and we are predicting some value. So I will be doing exactly the same. Maybe probably never execute this. Yeah, I never execute this. And I get this answer. So this answer is from a different method. That is, yeah, it's still linear. And here is just to show you both this one quickly. The same pattern that we follow and we will be following entirely with scikit-learn. We create the model, we create the machine, we feed the values. This is where the computation takes time. And after that, we predict what we predict here. We create the machine, we feed, we predict. And actually, I'm using this prediction here to trace a line on this regression. this one I should not much here. I will probably talk better about this. About the PCA. Well, this still, we will talk about this later, but at least this is a good moment to start introducing this concept. Again, we originally have 4 features. We would like to have, or to know if there is one or combination of those features that maximizes my variance. So contains more of the information about the data. And this is basically what we are doing here. So we are getting here this estimator, a PCA, and I would like to get 2 components of that. So reduce the 4 features into just 2 components. And it will answer me that those 2 components are this, exactly this. See, this value times this length plus this value times the second feature, original feature. This value times this value times this value. So with this, we are reducing the 4-dimensional problem in this 2-dimensional problem where we are maximizing the variance. We are maximizing the information that just those 2 elements, those 2 variables that are kind of artificially created as a linear combination of the original, put me the data in the better shape possible, just with them. So we will see with the digits how that is even better when we are moving from 700 something variables into just less than 100 with this. So just to get the idea, this is good for this very small example. This one here is same thing of k-means. This is just a classifying problem. So I am blind and not serving this. Here, the estimator, fitting, prediction of the means. The same logical machine. You will create this object with some arguments. We would like 3 clusters. This example here, I would like you to classify this in 3 clusters. Random seed, okay, 0. No computation is done at this point. No hard computation. Here is where the computation happens. After you have that, the machine just throw you answers. And I am using that to plot those 3 sets from the clustering perspective. So originally, the machine never knew that those are vertical or no. We are not giving that information. We are just we are clustering this one. So again, reinforcing the idea that is central to this workshop is everything in scikit-learn basically works under this model. You create the model, you fit, you predict. All estimators offer the fit. The supervised estimators can predict because they have an answer to predict. The unsupervised estimators, like clustering, they are only able to transform the data. So they are taking the original elements into other elements, and they can go back. So this is the basic structure for that. Okay, this is the first introduction to another example that I will use for other notebooks. But this is within a small set. So I will load in the digits. Let's see if I can get. This is a simplified version of the MDIS problem, NIST, where I have a smaller in number of instances, so they work faster, and they have 64 attributes, so it's a relatively small list. And I'm using this machine. We don't enter in the details what it means. It's just, this is the estimator. We are creating the estimator here. We are feeding this estimator with the data. And we use it to predict some values. I'm doing the prediction here. I'm comparing the prediction with the actual. We will not enter in more details. It's just the team, how everything here actually. There is something, for example, that this kind of things can do, is produce this kind of nice figure. Let me see, metrics. Again, the 3 steps are right here in the classical way, estimator, fitting, prediction. Here, I am plotting what is called a confusion matrix. It's showing me which elements I predict that were here, but they were actually from a different kind. So if everything is perfect, we see everything here purely black. If something is misclassified, we will gray areas. In particular, it seems that 2 and 8 for this example, for this case, for this super simplified digits problem, 2s and 8s are kind of difficult to separate. Not so. Again, this is a super simplified data set with 64 columns. So we can clearly see that with the confusion matrix. And this confusion matrix is also good for us to understand the concepts of accuracy, prediction, precision, recall, and a function called F1 that we will see later. Okay. Okay, now we'll use this confusion matrix to introduce something. Consider the nearest neighbors. Let's start with the most extreme case, the nearest neighbors. If you take the nearest neighbors problem and you ask, okay, what is the prediction for all the cases that I have in my neighbors with this machine? I will get 100% accuracy. Of course, because they have all the points. So the prediction for that point is that point. So that's one of the reasons why we always separate from our training data a portion to train the model, another portion what is called validation. So always split. The rule of thumb is 80-20. Everybody took the 80-20. So 80% to train, 20% for validation. You can do that better. We will see probably in a minute below. That when you are doing 80-20, you are wasting those 20 because you are not using them for training. So you are separating them. When you have a lot of data, you don't care. But still, some people can do something better. what is called cross-validation. For example, you can split 50-50, take the 50 here and validate with this, take the second 50 here as training and validate the first 50. Or you can divide in bunch of 10 and you have 9 here for training, 10 for validation, 90% for training, 10% for validation, and do all of that, selecting one of those 1/10 for validation and keeping the others, and moving cycling into all those. And Cycler is able to do all those things automatically. So they are able to perform those cross validations. And it's all, of course, able to separate from the whole data, training, a validation, and screw the data, so and mix the data, shuffle the data. Something that we need, for example, for the IRIS data set. If you just take the first 20, the first 80%, it will cover all the Setosa, all the versicolor, and a little portion of Virginica, and your validation will be entirely Virginica. So you don't want to do that. You need to shuffle that. Those numbers. So let's go back here. And exactly the idea that I offer you is, if you think that you use the nearest neighbors, not this, with the digits, and you just ask, oh, what is your accuracy with that training data? Oh, your accuracy is this one. It's 1%, 100%. Of course, all the data is inside the machine, so they know how to predict that. So we can split this, and this is the routine to split. It's in model selection. There are several routines here in model selection for shuffling mixing the data, for split the data, and for the cross validation. So all of them are on here. So here I am using this train test split. It will give me the columns for a training set, the features columns for a test set, the answers corresponding to the training set, the known answers for the test set. And this will be on 70/30. Okay. So now we can repeat this. And we see that our accuracy is 98%. We separate some of them. So for sure, there is a few of them that were misclassified. You can see that clearly from the confusion matrix. Should be around here and here. I'm not sure it's there. It's not clear from the figure back into the projector. But here there is something that I can see like a little bit gray, and here is something that I can see also a little bit gray. Yeah, you cannot see that. And so we got something slightly better. We have now a training set and test set and training set, and we measure accuracy. Keep in mind, keep in a grain of salt that accuracy is not what you will really want to use later on. Yeah.
But like, how did you know, or how did which method use for didn't you stick to your 9 to 10?
Here you control that here. 0.3. So here, this function takes that and returns the balance. And I think when we see, there is something that I'm not super sure about that, if they by default shuffle that or not. Mhm. Oh yeah, okay. It's not by default, but you can indicate that you want to shuffle the data. So, for example, in the case of the flowers, because in that data set it's 50 plus 50 plus 50, 50 plus 1, the class 0 plus 1 plus. So we need to use that. Otherwise, you will be doing awful things. So yeah, and there are some others split functions around there. Okay. Let's see. Okay. I will start mentioning this, and we will re-mention it later. Yeah. So we got here 98% accuracy, and now we will introduce why this is not good enough. So here we have another data set, randomly created values here with a normal distribution here, and more values here with another normal distribution, center in different points, and a bunch of zeros here, ones here. Okay, so this we split. I think by default is 820. And they have here what is called several scores. That this, okay, so here we have same thing. This is the estimator. Here is a little bit tricky. Here is estimator, and directly to this estimator, we apply the fitting on top of that. This is something that you can do in Python. We have an object, and we apply the operator directly on top of the object. It's just that we can do that in Python. And here is the prediction. So if you don't want to keep this object here, we can put the dot predict on top of that here and get the prediction. So you create the object, do the fitting, and get the prediction in one line. This. But after you do that, you can get an accuracy score, precision score, recall score, and F1 score. We will talk about that, what they mean. And here we have the test for validation, and the predictive value here. The test and the prediction for each of them. And we have those values. What is the meaning of that? Accuracy is simple. How many are correct? Okay. Precision. How many of those that you predict were the one kind, they were actually of that kind? This is one thing. Divided by that value plus those that you predict were of that kind, but they were not of that kind. We probably will see this actually better in the digits with one example that show this much clearer. But basically what we are doing here is looking at this confusion matrix and getting these values here are those that are of this kind, and they are actually of that kind. Here you have those that were misclassified because okay, here, this is the true one. Those here that, again, is hard to see, were misclassified. You say that they were of this prediction, you make this prediction, but they were actually here. So you sum all of those and you get those false positives. You get all those here and you get all those false negatives. And those values here are used to compute that. True positives are in the diagonal. False positives are sums in the columns and rows, and false negatives, columns and rows for that value that you want. The system is able to give you that, but it's good to know what they actually, how they are measured. Sums of this value. And here, the F1 is a balance between two. Different problems have different weights on what you want or what you believe is more important. Okay, first, precision and recall are in opposite sides of the balance. So you can increase precision at the expense of recall. You can increase recall at the expense of precision. That's one thing. So imagine, remember the figure with the logistic regression. When we move values here, we move the threshold here, we include more values that will now be correctly predicted, but we will include more values that will be wrong at the same time. So the balance is never for free. But the different problems put different weights on those things. The metaphor that I found really clear for me is, for example, in this video classification, right? If you are classifying videos and make a separation between videos that kids can see from those that kids cannot see, adult kind of videos, you are much better if you are able to, if you are satisfied misclassifying some videos that were actually not, that are actually for kids, and you classify them as adults videos, than the other way around. That's it. So at that moment, you want to preserve better the prediction, right? Another example is the opposite. You want something that is monitoring if someone is shoplifting, say with cameras. It's probably better if we don't embarrass ourselves trying to indicate someone with a false positive, right? From the perspective of the store, this guy will capture next time. But if we misclassify them in the other way, it's probably the best. So for the company. So different problems offer a different balance between precision and recall. And this F1 is trying basically to say how balanced they are. But it's actually the problem we indicate what is you actually want to sacrifice in order to get the other. And again, there is a nice example with the digits that will get this, not with this one, but with the digits a binary classification that we'll show you later. So here is the entire picture of the what it means: positives and false positives, true positives, true negatives, false negatives. And they have those metrics offered in one single table, the whole thing, for a classification or no. And just this one, again, this is still an introduction, so I'm mentioning different things in it. Apart from the splitting of the data that we are doing here, let me see. Okay, yeah, this is a 50-50. We can create two machines. They have to be two different machines. First, to use the first set for training and predict with the second one, or use the second one and predict with the first one. And we get those predictions here. And we can get an average. We can see how well we perform in those two scenarios. So the good thing is that we are actually using all the sets for both training and validation and separating into sets. But Scikit-Learn is able to do that automatically for you. So you don't have to do all those extra lines separating with this function. And it's using enough. So you put this function here, you put the first part, so the model, the machine, this tiny machine that is quick to create this one. We create here the entire set of values. And here is how many cross validations you want to do, how many times you want to split this. And this is the function that you want to use to get the scoring out of that. So the scoring will be the precision, could be the recall, with whatever you want to do. So it will compute with a portion of this X, a portion of this, and use the other portion for validation, get the precision, do the same the other way around, do exactly the same as this, but in just one function. And it will tell you the values in this. The same way, you can use a cross-validation object as a predictor. It will create a mixture where the values that are predicted are averages of the different subsets created during the split. So we will see that later. Let me see this one. I forgot to do something. Yes, yes. This one is similar. Cross-validation score. This is the tiny machine. The whole data, the whole answers, the known answers, a cross-validation with 5 splits, and I would like to see the precision. Precision, yes, the precision. And I'm plotting here the scores. Another thing that we can do is that you see most of those predictors, most of those estimators, they use parameters. In some of them we saw a gamma, and they have a default value, but tweaking that gamma with different values can give a better or worse performance. So sometimes you want to explore how they perform for different parameters. This grid search automatize that procedure for you. You can do it by hand if you like, and you can create with a loop with gamma equal to 0.5, 1, 1.5, blah, blah, blah. Or you can create this machine, this object, that will do that exploration for you. It's again in model selection, where they have the splittings, the cross-validation, all of them are in the same group of utilities for this kind of procedures. And this is the grid search cross-validation. So we have the machine. Machine is here, tiny machine. We have the range of values that we want to explore. We have here the range for the parameters. So this linear, this support vector classifier receives one parameter C. We will see later what it means. And we would like to explore all the values, 10 different values here, from minus 1.5 up to 2, 10 different values. It will start looking for each one of them, and we give you the best parameter under that search. Again, something that you can do it on your own, but if you know that this function exists, it's probably much better to do it with the function. At least you save some lines of code. And here we are getting the plot of that, checking the actually this value around here gives the best option. So again, we explore the different functionality around scikit-learn, the classifiers, the logistic regression, the linear regressions. We will start digging into those right now. We know there are now the utilities, the cross-validation, we will use that often, the splits, the loading the data. So now we will start looking into the different elements of of different areas of machine learning to get better idea of what they are. So we close this. This is a good moment for going for lunch, I think. We're returning an hour, and we will be working on classification, regression, and if we have time, clustering. We will see. And for tomorrow, we will be dealing with support virtual machines and PCA, dimensionality reduction. And there are more books that I'm preparing for. They're not included here for the neural networks, for the deep learning.
Do you think
Yeah.
grid search and these things explore or processors, like, or not? Because this doesn't make sense to do in series, right? You can.
No, there are some things that scikit-learn is able to do in parallel, in embarrassing parallelism. For example, probability search. They think that they have one option where the different, for example, the 10 instances run in batches, right? Using the different cores on the machine. But not for everything here is parallelized. So what is well parallelized are the kind of things that we will see tomorrow. For the deep learning, the neural networks, yes, those things are fancy, they're time consuming, and they have to be parallelized. And hopefully you can use even the GPUs instead of relying on the CPUs. So yes, for those, yes. Yes. What? For lunch, this thing is paid. So we are going for lunch. 1 hour.
It failed.
Well, I don't know. Well,
Let me.
yeah, it's finished. But maybe it's already, so we can just shoot down.
That's fine.
Well, let me. Is it done this? Wouldn't it just do it just now?
Yes. Maybe it's too hot. What's too hot? We were closing. We were closing the session, and we were. So we return in 1 hour.
Well, I want to make sure, because you said it was doing this last week too. So while it's doing it, I want to take a look at it.
I don't know how to.
Think it's all right.
Yeah, so far so good.
So there's a bottom mistake.
I need to balance because now I need to know that during the morning I can cover this.
Well, I have,
And
but I have to manually run that.
how far I can go. This is the first time that
No. When you say they only do the parking tickets there.
Okay.
Well,
You guys
normally,
said you make it on that break.
I could,
So what do you plan?
So the Jupiter Hub instance was my mistake. I didn't take, because that instance does not generate usernames. So I created them all, but I didn't create one really zero. So if they were logging in with training 100, they were fine.
All
But
my
it wasn't 0, 50.
current running. Make sure my.
Okay.
But I fixed, I turned off there's
Yeah.
called
Okay, let's
curling.
see, 'cause I.
So yeah,
So it shouldn't be, you shouldn't have had issues anymore with killing the kernel. Has that been better?
no. Well, it just crashed once
Yeah, at the very beginning.
at the very beginning.
Yeah, I fixed it after that.
And then after that, it was this machine is perfect. I'm no complaints with this. It's good.
You were easily.
I'm pretty sure it was still at least 1 or 2 years left. I wonder if it's gonna finish or not.
Did you took a machine learning class?
Yeah.
Oh,
We've taken the parallel class.
the class with Aldo.
Yeah.
You also, you want this, the graph that survived.
We all.
We are trying to
all
grip the
survivors.
survive, yeah, pretty much.
All 3 of us, everyone else quit.
Yeah. At least
Apart from that.
Only you, or more people from.
From our lab,
like 6.
from our lab, we started 6 of us and ended up being just us 3.
You came later.
From our lab,
Yeah.
yeah.
But I think we started with like 25 people total, and I think we ended up with like 9 or something like that.
But you never took a class on machine learning. No?
Oh, exactly. Yeah, we've used a couple.
It's because I
Used
used
a couple methods.
Okay. It's because we have, I don't know if you remember, or you are familiar with Gihan from James Lewis group or Arturo. They were no. Okay. They took a class in machine learning or something like that. Computer science. From computer science. So they registered for that as a credit class. They used that during the thesis. Yeah. They both graduated. They both used. Arturo was using neural networks to predict energies. Basically, this was some potential design. So how to predict the energies of unknown structures. And Gehan was using random forests for predict catalytic properties of clusters.
That's really cool.
So
Yeah.
so that they both got
Like
away.
very dubious of like to shows the structure and then suppose
Yeah,
the
so
structure test it out.
so basically you have a cluster and they can attach in different places. They have several ligands and they are basically predicting which ligands or which structure for that cluster because they have different metal atoms inside. give better catalytic properties, better bonding.
I've seen similar things done for like ligand testing.
Yeah.
Making new ligands.
So you can see the lights are
test
on.
the-
Yeah, so those are very.
And these
specific.
weren't
Good thing
going
is
as before.
that even
Those are
if you don't
flashing.
get super
I don't know
amazing
what that thing
results,
is at all.
yeah, you will need a lot of data. The fact that you are applying machine learning into chemistry problems
We're projecting for the
is
PC.
really fascinating.
Yeah.
So even if it's just exploratory.
Yeah.
Okay.
It's like, so like, I don't, if I really know, it's the. So that I'm not confusion, like I was thinking, that's what. Probably I made this.
See, but we're talking about your mission possible hang on.
Or, yeah, and I was already freaking out when he was in the other room, that it was
Okay, so now we will try to cover now specific topics in machine learning. And we will start with classification. We already did part of that, but we will concentrate on this. Again, this comes from several sources. And now, this is the first thing that I will do for this next 2 or 3 notebooks. Is always start from where we are in this map. This is a figure, from scikit-learn. They have it there. So they have a nice thing where you follow this and you try to see what exactly you want to use, or what you need to use for the kind of problem that you have. So we will be talking about this pink, red, light red area right now. After that, we will be talking about this one and this one. Not sure if we will deal with this today or tomorrow. And this one for sure. The PCA will be for tomorrow. So let's work on this. Classification. Classification and regression are basically the same thing, except for classification is for categorical output instead of a continuous output like regression. So it depends on the research, but classification is not much what I do. Regression is probably more relevant. And we will start with this classical problem. Again, classical problems, those are easy. Nice data, clean. I did this. And the good thing is that we will use this to get a better understanding later, again, to these concepts of precision, recall, and F1s. So this one is like this. It's a set of 70,000 images of handwritten digits. So they think coming from like 200 people, some people high schoolers, some other people employees from this list. Collections of handwritten digits. And the problem was used to classify mail, to classify zip codes, basically, for the post office. That was the original purpose of this kind of data sets. And we will see how good we can, how far we can get with this. So, okay, so here it is from the data sets. I'm using this fetch OpenML. As I told you, it's coming from this data from the OpenML, specifically this data set, version 1, and I'm downloading the code. Keys are this, and we will see the data, how it looks like. 70,000 instances, and each one of them is an image. It means that it's an image of 28 times 28. So tiny little image, right? No colors. I will plot with some colors just for visualization. It becomes better, but no colors in this image. So each pixel in those 28 times 28 contains a value from 0 to 255. 255. That's what it is. Okay, so this is a look. This is plot of the first 12 digits. How that look like? Huh? It's not working. Let me see.
BLT is not defined.
Which one is not defined?
Oh, it's just the set. You need to.
Maybe there is something in the very top.
I'll talk about that.
So the first 12 digits. This is another thing that is very particular for machine learning. You are dealing with a problem that is trivial for a human to solve, not so trivial for a machine to solve. And we will use, we see a classifier to figure it out which digits are here. So the idea is it's really, really clean on how we get this solved. Let's see, for example, the first 12 answers from the, so this is again, this is a problem in supervised machine learning. So we know the answers. At least for those 70,000, we know the answers. So you see that the numbers match what they should be for a human to check on them, right? We will do this change here to the values. Originally, the numbers are this type, and we are changing this to just integers. Small change. Saves a little bit of memory, but that's not a problem. What I'm doing here. Finally. Okay, so here is a view in actually black and white of the first 100, 10 times 10. All the digits, just for you to get an idea how they look, how twisted. Yeah.
I have a problem again. What digits is not defined?
Let me see. Check what is not defined.
Block digits.
Block digits.
No, not index. Go down. This one. Yeah.
Block, did you execute this one? Oh, yeah. Do you execute this one or this one? This one is just for plotting one.
Yeah.
This one is for plotting the whole array, the grid. And those two are working together to produce this big image. So you see, something's interesting. Let's say for Americans, this is the way Americans write 7. For people in Latin America, at least from a country, people used to write 7 this way. So they are captured a cultural difference even in the numbers. So yeah. And here we are separating by hand. We are not using the split function, but this is simple. The first 60,000 for training, and we will use what is left, so 10,000 for validation, right? So this is how we separate this set here. So this is a tuple here. So each element is receiving the corresponding element here. Okay. And we will start working on a simplified version of this problem. Not classifying the 10 digits, but we will classify just for 1 digit. A simple problem. So we will classify for the elements that are 5 and those elements that are not 5. So we are reducing the problem. And a lot of interesting things will come out from using this particular selection. We will use this stochastic gradient descent classifier. This is one of the several classifiers implemented in scikit-learn. This classifier uses these arguments: certain tolerance, number of iterations. This is basically a local minimization algorithm where not the entire elements are present. So a random selection of elements is meaningless. We will not enter in these details because my objective is slightly different. So the tiny little machine, and we are feeding the data, right? And here we are predicting the data. The answer is basically if something is 5 or is not 5, right? And we see that our prediction for these elements using this algorithm for classification pretty much works, it's working, at least for these first 12 elements. The first element is 5, okay, that's okay. Compared with the known answers. So yes, this is 5. Yes, the last one is 5. All the elements in between are not 5. Okay. So now we can start looking into better understanding of what accuracy, precision, recall actually means in this. So we have accuracy. How many right answers versus the total number of cases that we have. So what we get, oh, I forgot to do something. Oh, that was,
So that's it.
yeah, I probably forgot to execute this one.
Oh, I got a memory error.
Memory error?
Yes.
It's because I forgot to create this object. Let me see. My memory is not that bad. I get in 600 or 1 megabyte.
Me too.
The memory is growing a little bit, but how much memory do we have? 16, right?
Yeah, you're getting close to using all of it.
No, not close. Or close.
Close.
Ah. Yeah, too many people using 1 gigabyte. Yeah. Well, we'll see. Otherwise, we shorten the size of. You are getting issues with memory. Okay, let
Yeah.
kick you out. Okay, okay.
Is it working for you?
Yeah, at least at that point, yes. Here,
No, go
but
like go down.
But I don't want to
I
keep.
have error on this one. Yeah.
No, this one is because I never execute that.
Mine is memory error.
But yeah, I could get an error here. So what I will do is this. I will not be that bad if I sacrifice a little bit this. Let me see. Yeah. Yeah, like this. That is a cheap solution. Actually, instead of 60,000, I will just take 6,000. My points will be the same. I will get probably worse performance, but everything should be fine, and I will not cross the memory. And if all of you are doing this, the memory footprint for everybody will be better.
You're taking 6,000, and what is the 6,000?
So here I'm taking 6,000, the first 6,000 for training.
Okay. Texas test.
And yes, and to keep something reasonable here, I will probably change this to 66. So I will be taking 4,000 for testing. So I am removing the first 6,000 here and the last 4,000 for training. I'm skipping all the elements in the middle. So and the elements are already shuffled, so I don't care much. That will get faster results, and that's probably what we actually want. Okay, now it's super fast. It's okay? It's working for you? Okay, so now so we got an accuracy of 96%. Right? 96, yeah. And here we are doing cross-validation. See that I'm using the cross-validation. So this is an average using the first set, the second set, so dividing this training in 3 and validating those cyclically. So okay, we got this. Now imagine that I will create a fake, entirely fake estimator. An estimator out of my hat that I will create on top of this. And this estimator will say no to any number any image that you give me. I will say, this is not a 5. This is not a 5. It will answer negatively every single time, right? And here I am using this never 5 classifier that always answers no, no, no. What is my accuracy? 91%, which makes sense, right? Because one of every 10 digits will be 5, and saying no will be fine for the 90% of them. So this classifier that also always answers no, it's not a 5, will be right 9 of every 10 times in average, right? So accuracy is not a good measure for how good a classifier is. So we can get a better idea, and we already did this. Now we're entering a little bit better into this concept of the confusion matrix. So the confusion matrix here, it will be very simple because it's just a matrix 2 times 2. So we define, okay, let's first have a look at this here, how this matrix, so now we have just 6,000. So this matrix is, the values will be smaller than what we used to have. So let's interpret first the values inside the matrix, and we will correlate with the meanings of the positives, the trues and false. Here are values that are not 5s, and they are actually not 5s. So everything else. So true negatives, those are called true negatives. Not 5s, and they are classified as not 5s. This one, those are values that are 5, and they will classify as 5. Right? So here, 28. Those are values that are, I think, is predict. Yeah. So yeah, I think it's predict in the x direction, actual on the y direction. So it's predicted not to be 5, and it was actually 5. Right? So those are false negatives. And here are values that are predicted to be 5, but they were not actually 5. They were something else. Okay, yeah. And what happens with this one? We offer the same training set as input. We will get everything perfect. We will get this confusion matrix. So this number of elements are not 5. This number of elements are 5 in the set. And we will use these values and these values to understand the precision recall and F1. So precision, number of true positives divided by the true positives plus false positives. So here I collect those, but the numbers will change slightly. So this is what we get. Those are the numbers when I consider the entire set. So those have no meaning right here. And this is the recall. Recall, number of true positives, so numbers that we predict that were 5 and that were actually 5, divided by that number plus numbers that that we predict not being 5 and they are actually 5. I have to think that all. And this is the F1, the balance, the equation that is balancing how much precision and recall you have in your set. And the values here. So again, don't pay attention to those values. Those values are only valid when we took all the score. So you notice why we're getting those values so counterintuitively. we have an extreme imbalance between the two sets. We have one of every 10 values are 5, 9 of every 10 of them are not 5. That imbalance of values raise the difference between accuracy and precision, and the meaning of them. And the meaning of them is very clear from this 2 times 2 matrix that we have. Okay. This function, at least for this estimator, is able to give me a value that scores how to put a number that is used to decide if the number is actually 5 or not 5. The meaning is if the value is positive for this decision function, it will not be considered, if it's positive, it will consider 5. If it's negative, it will consider that it's not 5. And we see that from our first 12 elements in the training set, that this is positive, all those up to here are negatives, right? And those matches. So this classifier is able to give me an extra function, that is this, the decision function. Not all of them offers this kind of functionality, but for this kind of algorithm, they have this, they score how close. So values that are really close to 0, we're kind of in doubt. If you move a little bit the bar, the threshold bar, it will probably be classified in a different set. So now what happens if we change the threshold? We are not able to change it in the algorithm itself, but we can artificially change the threshold using these values here. From these values here, we can manipulate the threshold. So right now, with the threshold set up 0, as the algorithm normally works.
So just a question. So decision function is something before threshold inside the algorithm. That's it.
It's something inside. It's something that this estimator is able to give me for every single instance.
This is before deciding. It's some internal information.
It's after feeding. Yeah. So you create the machine, you create the estimator, you feed the values,
right.
And now for every value that you give me, I can give you a number,
right,
that estimates, that offers a value.
So the threshold usually is 0.
The threshold internally is 0. We are not able to change the threshold inside the predictor, the estimator. So we will fake it. We will use those numbers to see if I move into this direction. But basically, what I would like to reach, or what I like to show you, is exactly the same thing that I show in the logistic regression. I move my threshold, and I add in more false positives into true positives, into true negatives, sorry, and more true false negatives into true positives. So, and both things comes together. So I am lowering, I can improving my precision at the expenses of my recall. That's the main message. So that's what I would like to reach at the end. Okay, so I will be changing the threshold. I imagine that my function was able to move this and give a different number. So everything is fine here if my threshold is this. In my threshold is higher here. It's also because the numbers have changed extremely. So what happens if I use a value there sufficiently high? See, value is extremely high. It will say nothing is fine. Nothing qualifies to be a 5. I moderate that a little bit. Okay, how much I have to moderate? To 200. Oh yeah. Well, this. Oh no, it's too much. Okay. Yeah. I move the threshold up to 6,000, 60,000, and only this digit qualifies to be a 5. And so this one will be a false negative in this context. So now let's see what happens here. I will be using this. The thing is that probably have to change this. It's like, it's too far for the values that were originally created. That's the point.
Okay. Shut up.
Yeah, those values will not calibrate well. What I can do. I am trying to fix this by hand. Let's see. Almost captured the idea. Anyway, the decision functions have changed, so I have to tweak a little bit the numbers. So don't worry about these points here being in the wrong location. The idea is that I can increase my precision, but always decreasing my recall. So I can include more elements that into true 5s, but I will add in more elements that are not, that I will classify as 5, that will not be actually 5. So those two things always are in contraposition. So let's see something else. We'll probably face this all the time with this. Yeah. So there is a balance here, again, between precision and recall. I can maximize one and expense the other. And we can see what is the threshold that I have to use in order to set up my precision up to 90%. And this one. So I have to move the number of the threshold up to here to get 90% precision. But at that moment, my recall will be lower to just 56%. So one thing changed the other. That's the main message of this, of what I was trying to do at that moment. there are some other things here. The next thing. That balance again, it's a similar curve. What is called the balance between specificity and sensitivity. How good you are selecting things in one way or another. Again, remember the problem that I told you about movies and that are not meant for children, and you prefer to misclassify very conservatively. And from the other point of view, if it's just the camera looking for shoplifters, you also want to, you prefer to be negative in some instances, just to not embarrass yourself with values. So here is how this kind of curves looks like. I will probably get several of those points misplaced as I change the number of instances. Let me see. Yeah, point is not exactly here, but you see the idea. Different estimators will give a different balance between those 12. Okay, not much to see. I think, yeah. Now we can skip. Okay, this is just the last part of the topic. So we saw one classifier, and this classifier is able to give just one answer. Sometimes binaries, sometimes you want classifiers that also give you an entire range of categories as output. In this case, what we have here is, let me see. Okay, here. Let me see what I'm doing. Okay, forget about this. This is my mistake that I copy and paste this message. I am taking the numbers, I'm taking all the digits. So my prediction here for the first elements are actually the digits. I'm checking that they are predicting this correctly. And just copy and paste one. And I have 10 classes here in this classifier. By the way, this other classifier, so this is the second classifier that I'm using here, is a support vector. That we will see that later. What is the idea behind support vectors? So a different classifier, same thing. The values change too much. Okay. So now this time, with this classifier, I get this confusion matrix. All the elements in the diagonal are here. So this time we are now classifying the 10 digits completely. And we can see that with Matplotlib as an image, as a matrix. It looks like this. So we see all the numbers that are out of the plane, misclassified, all out of the this is another way of looking at that. Nothing outstanding. And those are basically all the digits predicted in the different sets. So consider this as a matrix. So all those that were classified as 3, all those that were classified as 5, all those that were classified as 3, but they're actually 5, all those that were classified as 5 for some reason, and they are actually 3s. So misclassifications, right classification. You see that, yeah, you can even see a little bit why maybe this number was not actually, was close to 5. Yeah, why then those machines become confused with those kind of things. Okay, so this is what I was doing here was showing a classification multi-class. So we move from binary classification to a multi-classification, and finally multi-label classification. In that case, it's not just one answer. We have several answers so several different categories. And the example here is if the number is bigger than 7, is one label, and if the number is odd or even, is another label. So we have 2 columns in our knowledge, in the known labels this time, and we are using this label and this label to classify this, and we are using this key neighbor. So a very simple classifier. So the first elements here are, this is the prediction, and I forgot to put the labels. Okay. Yeah, probably we need to do something like this. Yeah, and now we get there. Okay. So this column is saying if the number is bigger than 7. Bigger than 7? Bigger or equal to 7. Greater or equal to 7. This one. So this number, it says true, is probably this one, right? And this number is a label here for if the number is odd or even, right? So you get a bunch of odd numbers, you get an even number here. What is this? Oh yeah, odd number here, odd number here. All of them except for some even numbers here. 4, 2, here, 2, and 0 classified. Okay. So now we have a classifier with 2 columns in the labels, and it works. Not all of them support, not all classifiers support this kind of multi-label classification. And this is the scope for. Now they have this one. This one is tricky. Let me see that. Okay. This is what I'm doing. I am creating a version of the image that contains some extra noise. So I am adding some color, extra gray values here. Very tiny, a tiny value, but it's still is. For the training, for the test. So I am testing how much noise I can add to that, to those numbers, and still getting the right answer. And here, I'm getting the function backwards. So I am cleaning the digits. Let's see. Okay. In summary, before we move to the next one, we were working with this one, SVC. We work with this one, with the stochastic gradient descent, and SVC, and we use also this one here, the k-neighbors classifier. So we covered all those here. The naive base is more for text, so yeah. Usually use either this one or this one when you want to do classification. So now we have one example for each in this note. Let's move into the next one, and we will have some time for exploring. Let me see. Okay, let's cover this one for regression. This time the output is a real number, or is a continuous value. Basically. That's the idea. So we will be working on this other area, this blue area. There are several algorithms here for regression. Most of them are evolved from the linear regression as a prototype, even if they cover more than just linear. We will see that in a minute. So regression analysis. Basically here we are predicting continuous variables. In linear regression, that is the first one, the classic example of this. We are lucky, so lucky that we don't need actually machine learning for solving this problem. So this is the kind of problems that you don't use machine learning, at least in principle. In practice, you use machine learning, but for some other reason. They are basically trying to minimize the vertical distance in those points with a line. This is the idea behind the linear regression. So you have a bunch of points here. I create those with a randomization here, small random number. And the question is, what is the best line that fits those points in the plot? Well, the idea is to have something that accounts for how bad we are in this. And the function for accounting for that is this one. It's basically the vertical distance in those points, the vertical distance, how bad we are in the prediction. And the reason why it's bad for machine learning is that we have an equation that should be around this one here. That is basically a linear algebra operation. With a linear algebra operation, you get that the slope and intercept cleanly. And this is basically what this linear regression is doing. So linear regression actually works on top of SciPy, and is doing the operation. What is that? Yeah, I put it here, but without the equation. Okay, is this? This is the operation, a pure linear algebra operation. The inverse of this matrix transpose dot product with this matrix dot product with this one transpose product dot product with this. So there is a closed form for the least squares. So that's why you will never use actually this with machine learning. But there is a price for that. It's slow or too expensive if the number of features is too big. So that's why there are better options, and we will see that. Oh yeah, here. Right here. So SciPy offers that function for you. Exactly. It's exactly the same thing. So linear regression is just actually using this, but put in the form of estimate, and basically produce exactly the same results. What I'm getting is. Probably because I never initialized the random number generator. I'm getting a slightly different result. But, yeah. So you can do it just with pure linear algebra. You don't need machine learning for this kind of problem. And this is the equation. This is what I show you there in NumPy. It's just this. There is a better way when the dimension is large, and it's this one with batch gradient descent. Instead of using the whole points in the set, you use just a small subset of points to compute the gradients and follow the gradients to optimize the curve. And I have here some examples of. Okay, yes. So you see here, what is the correctness? There is a parameter, eta, that controls how fast you move into the gradient. It's basically computing for a few points after, a few points before, a few points one side, another side in the 4 dimensions, to get an idea of the gradient, to get an idea where it should move to improve the cost function of this. So if you start from here, this slowly start moving into this direction. But this parameter is so small that the movement into the gradient is very, very small. Again, this is not using the closed formula. This starts with a random assumption of what should be the slope and the intercept, and it will start moving into the gradient, finding the optimal solution. But this value is too small for that. This value is probably much better. It's actually, yeah, it's much better. We start here, and it quickly move into what we see here looks like a reasonable linear regression for this problem. And this one, the eta is so high that it basically jumps back and forth into the 2 extremes. So you have the slope here, and the gradient is followed so much that you jump into the other side of the valley, in the other part of the mountain, and you go back and you jump, and you get lost eventually. So this one is what people actually uses for this kind of problem, is this Bayes gradient descent. And this one is an evolution of this other case. That instead of using the hole, use just a push. Same thing. I don't remember which eta I set up for this. And it produces exactly the same result that we found, or at least very close to the result that we found with the linear regression. Yeah. So we explored 3 different methods. All of them basically converge to the same values. 4.1 to 0.8, 4.1 to 0.8, all of them 4.1, yeah, 4.1 to 0.8. The linear regression, the stochastic, and the batch gradient. Okay, this one is interesting. We will put to compete the 3 different algorithms here. Again, the values. So this one uses a small subsets to compute the gradient. So it's very efficient. It's not using the whole set as the linear, and it converges nicely. This one, the stochastic, uses just one element, so it bounces a lot back and forth between the solutions. And this one uses a very tiny set, so it still bounces a lot. So usually people use the batch. The batch regression. Now, not all the problems are linear or they behave linearly, but there is a trick commonly used in machine learning to reconvert non-linear problems into polynomial problems. The trick is basically adding extra features that account for the non-linearity of the problem. And after you treat them as independent variables, and you get the solution for them. So it's much better if you see visually what we are doing here. Let's start with this. Same number. And I will create a function with some randomness here that is quadratic. So you will see how that looks like. This is the function. They have some randomness here, back and forth. So you know for sure that a linear regression will not work in this case. No way. However, you can consider this x and create a new feature that is x squared. And if you like, a new feature that is x cubed. And after, forget about that this is x squared and this is, and put a different name. Let's say x1, x2, x3, x3. Label with a different name and treat it as independent variables and apply linear regressors to them. So that's exactly what this pre-processing function here, the polynomial feature, does for you. So if you have one single variable, it will be extremely easy. We'll create x squared, x3, x to 3 power, x4. If you have two variables, it will create x squared, y squared, x times y. It will create all the non-linear terms additional to that. It will add them as separate features to the system. So you will see here that is adding the original value. I don't know what. It's one of those. And a value for the square. You apply linear regression, you apply the machinery that we know for linear regression, as if the system had that extra variables, and you reconvert, you go back to recover the single value that you have, and you have created a non-linear regression estimator with this simple trick. So now the question is, and this goes into the course of dimensionality, how far should I go? If I don't know that this is a quadratic, why I never went into a 3, 4, 5, 6 higher dimension for this? So there is a problem, and there is a solution for that. Oh, wait, this is not right. Oh, I forgot somewhere. Oh. Oh, okay. I don't know where, but I forgot something to execute. Okay, so here this figure is showing the original points, the same points that we create with this quadratic equation with some randomness. So the linear regression will give me this. This is the linear regression. Doesn't work. The quadratic, applying this trick, we get this blue line here. But what happens if we ask for 300 power, 300 dimension? We get this awful curve. It's trying to fit better, but at the end we get this this bouncing behavior here. So it's the same thing that we see often when you try to when you try to fit points to a curve. If you have enough points, you can fit an elephant with them, right? And there are some techniques to tame those extra dimensions to control them, to allow them to exist, but not allow them to go wild. The usual trick, and this is exactly the same what we will do for the different versions of this, is to modify the cost function in the linear regression with an extra terms that weights those extra, that weights the contribution of extra dimensions in the non-linearity, the non-linear terms in the equation. So this is one of them. So we will consider this. We will consider exactly the same. These same points, we will use the 300 dimension of polynomial, ordered polynomial, and we will control it with this. So if many of those elements becomes high, this function is high, and this solution is not acceptable. It will try to minimize the number of values that are high, too high in this set. So I will plot it here. Yeah. Okay. This is with this regularization, rich. Yes?
I just wondered, I understand how you're using these methods. Is there ever, or is it commonly used that they do like a step linear function as opposed to like a solid function? You know what I mean? Like a linear function with cusps, like two faces together instead of like
a discontinuous function?
Yeah, pretty much.
Or this discontinuous or not?
Not discontinuous, just
The derivative will not be continuous. Or what? Yeah, exactly. Well, not here, as far as I know. All those are continuous things. There is one at the end that it basically applies a different trick that is nice. It just evaluates the outcome and it stops. So it just stops when your solution starts getting worse. But yeah, it's an artificial stop of that. I don't know if that translates exactly as you say, but so those first are purely continuous. So how they work. So this way.
I mean, it's a stepwise function, but it's continuous, but not continuous. Derivative continuous.
Yeah, it's not smooth enough. It's not a smooth function. Continuous and derivative continuous, a second derivative. So okay, so this one and the trick here, just to see what it. So all this is just for the plotting of this. I am controlling this alpha again, 300 dimensions. So I have those points here. But I have a new parameter here to control this alpha. So how much I wait not to add extra nonlinearity to the system with this alpha. So if the alpha is 0, we go back. With alpha 0, we go back to the normal 300 dimension problem, right? When alpha is high, we wait a lot, and we will force to go back into the linear regression. Kind of, the limit will be going to the linear regression, and that's exactly what you see here in this curve. So for this subset, setting alpha to 0 will go wild. Will start moving up and down. When we wait with a relatively small value, it tends to start controlling this wavelength of data. when we weight this, you see that for most part this is a linear equation, and it escapes and tries to capture here the value. So in this figure, it will behave like a linear for most part, and after it goes up at some point. So this is one regularization procedure, and this is visually what it's actually doing. And those are extreme cases. So this is alpha is 100. So it will penalize so much the nonlinearity in the system that will produce basically the linear regression.
What is possibilities for this alpha? Can it go more than 100, or is it just between 0 and 100, like probability?
The what?
Alpha.
The alpha, I think that they don't have no constraint. So I see that 100 is indistinguishable from the linear regression. So 100 is too high. So let's see the string. Let's see the equation, and we understand from the equation. Or let's go back here. We are using the green line, is that right? If we apply this trick, we have this is a function of x, right? It's a function of just one variable. Yes. But we are creating a 300 extra fake variables that we don't say that they are different. One is for x squared, x3, x23, x4, 5, 6, up to x to the 300 power, right? So 300 different variables. We will treat them as different, and we will apply a linear regression from them. And the result, we come back and take this for plotting just one variable, because this is a one variable. So we will get this. We will get this green line going up and down, trying to fit this elephant with 300 variables on there. So it goes wild. We apply this function with this is the minimal, the least square, normal, but we add this alpha times and the squares of those parameters, all those weights. Each one of those have a weight in the polynomial, and we are basically taking the square in order to get a positive number, and we sum all of them and we multiply by alpha, and that will be the weight and the cost function of that solution in the linear in this linear regression. So you see, if there are too many values here that are big, this quantity here is big, and this solution will not be accepted, and the local minimizer, the steepest gradient descent will follow a different path, because this is not a minimum. We can consider two situations here. When alpha is 0, we go back into the first case, the wild thing. So the green line here, wild. And we can consider the other extreme of this equation is alpha going into infinity. So if alpha is high enough, large, this will weight so heavily that it will not allow basically any of those elements to become different from 0, right? And that's exactly what we see here in those two figures. So here we explore the alpha equal to 0, at least for those points, just for those points here. It will go this way. When alpha goes to 100, it's basically a straight line. It's just a line, right? It's clear that idea of the alphas. Okay. So this is basically like a line. Okay. Yes, it's clear the idea. So, okay. They have this. This is not You can include this penalty in the regressor for this one. This is not 1. This it's kind of misleading, but this is not 1. This is L2, and this is how you declare which kind of penalty are you using in this case. So yeah, so you can insert that into the you can use this regularization.
Can we see data? The parameters?
Let me see. I'm not really sure if we get. Let me see. You mean the weights? Do you want to see the weights in the polynomial?
Yes. Parameters I'm trying to find, right?
Yes, yes. But let's say here I'm just looking at the prediction. So let me see if I can get that here. But this is not. No. It's returning, but it's just returning the coefficient for the variable when it's back converted. It's not. They should have a way of getting that, but I have to look at the documentation how to get all the weight. So I imagine that what you want to see is the 300 weights, right? You want to see the 300 weights and check that they are basically 0.
Right.
That all of them except for 1 is actually 0. But as everything is hidden in the machinery, I think that there is a way of getting those. But yeah, I have to look. At least the coefficient is just given there, not what I was expecting. And the intercepts, they are not given. Yeah, give me a minute later when we go through the exercises and I share for that. So there is another one here, the lasso regression. And compare this equation here. They have an alpha. They don't have the 1/2. But the only difference here is that they weigh differently here. It's just the absolute value instead of summing the square. So those two are similar. The idea here is that you have a positive value. You don't want that a weight here positive compensates here the weight that is negative. So you need all of them positive. You have two choices. Or either you put this in absolute value, this is one option, or you make a squares as we did for the ridge. So in this case, we have 1/2 that can be absorbed in the alpha, but traditionally is like that. Or here for the lasso. So this time is like this. for this 0 points. Probably this one is better. Alpha, again, alpha equal to 0. We are removing that. We are returning into the wild situation. A very small, even a very small, but non-zero quantity on the alpha change the behavior quite a lot. Regularizes the weight. An alpha equal to 1 will basically return a straight line. So okay, there is this one. This is the third regularization. In this case, it has 2 elements here. So it has a little bit of lasso here and a little bit of reach here. So both of them produce positive numbers. So all of them are weighting in a balance. So if R is equal to 0, you return to something that is like less, like reach. If R is equal to 1, you return to lasso. So it's in the middle. So you have a parameter that allows you to move continuously between lasso and reach and backward. You see, this R is controlling both that thing from one place to another. What I did. Okay. I have a log here on this book. On this set, I forgot to import this, so that is why it's not working. So I fixed this line. I forgot to add this line. Okay. Anyway, and there is this other idea of stop the training when the validation. So you have your training and you have a validation set here, and you start using this regression until your validation becomes worse. The value that you measure for the validation goes bad. So, and that makes sense from a very visual point of view. If you have something like this, you imagine that not all the points are here. So you have some of those points that you don't see here because those are the validation set. When you start using something that waves like this, that is so wild, your errors will be huge. So at the very beginning, when you start moving in the curve, you will improve. When the polynomial start wiggling, you start getting worse, bad results, and that's the point where it starts cutting the algorithm. So this is the idea of the early stopping. Let me see if I get this. why I'm getting this. Oh. Like this. This is the idea. When your model start going bad, you stop. And here are some examples of lasso, reach, and the different parameters. We will complete the picture here briefly because we already did this for the IDs, data set. The logistic regression, that is a classifier. With this completes. Okay. Okay, we can go into this one. Yes. Okay, so we will have time for this one probably relatively fast, and we move this for tomorrow. Clustering. Okay, we'll probably not execute this one, just see the data that's here. Okay, this one is right here in this map. We will be covering the k-means, the mini batch k-means, and maybe this one, the spectrum. So this is the idea. This is a completely different problem from before. We have the data. We don't have right solutions. We don't have, they never give us any solution of anything. The idea is not predict outcomes. It's just to find a structure, find what is in there. At the end, this is one of the first things that you do when you are doing machine learning. This one, in combination with dimensional reduction, PCA, this is what you start working on. You start getting the data and see what the structure the data offers out of hand. So you have a lot of columns, and you start picturing how I can classify, how I can group, cluster the different variables in the set. That's one thing. Second thing is usually get too many dimensions, and I don't want to work with all of them, so I reduce the dimensionality of the problem the best that I can to manage. And after I start working with classifiers, with regression, even with neural networks, deep learning, all the stuff. This is one of the first stages in the analysis of the data. So imagine that you receive a data like this. And just if you are lucky and you just have 2 dimensions, you can immediately see, oh, okay, here these have three different clusters here. So yeah, so we can identify those quickly. When you have 50 dimensions, it's not visually possible to know that. So consider this example, again, the iris. Imagine that you are blind, so you don't get those nice colors. You get this. You get those 2 sets, those points here for those values. So the best that you will do is, oh yeah, it looks like you have 2 clusters there, right? 2 different species for those flowers. But if you include more dimensions, you will see that the algorithm can actually see through it. So we will use in this Gaussian mixture. I never put it here. What is the condition? It's not in the map here, but this is another. This cluster is able to identify those 3 clusters. Okay, but I prefer this. K-means cluster. The idea is nice. You receive all those points in a space, imagining high dimensional space, and you start imagining that you throw a certain number of centers, completely random, and you start measuring for all the different elements in the point, where are the centroids of them, and move this central point into that centroid, and repeat the procedure for the next one. So this is called the K-means, is the classical example of a machine learning for clustering. So in the first step, you assign a set of centers. Now you assign points to those centers. You compute the Euclidean distance between them, and you, from that Euclidean distance, you compute the center of gravity of that set of points, and you get a new point. And you use that to repeat that procedure until you get a stable situation. You converge all those points into the sets. What happens, for example, if you have something like 3 of them and you throw 10 different centers, some of them collide into the same location. So you get a few points here that are actually the same. What happens if you put just 2 of them, and for something like this, one of them will probably go here, another will sit in the middle, probably around here, balance between those 2. So maybe probably can do this. I will execute it here. So here I'm faking one example, one. 3 sets here, some of them here, mix. This is how you import this evaluator here. You decide here how many clusters do you want to make. This one is again to avoid randomness, fake the same random numbers all over again. And it will produce a classification of the points. So you will get a number here for every single instance, and all of them correspond to the different points that you classify. So you classify asking for 5, so you get numbers that goes from 0 to 4 right here. You can label them, and you can plot those things here. Let me see if I, yeah, sure. Yeah. This is what the system is doing. Well, actually, well, you throw the points. You decide that you want 5 centers. You can change that and put more centers. That's more. Some of them will probably coalesce. It will select the center of mass. It will move into that location. Will compute again, until you get this collection here. All those points here belong to this one, to this center of gravity. All those belong to this center of gravity. All of them belong to this one and this one and this one. What I'm doing here is calling the Voronoi diagram for those points, for the centers, to decide which are the areas that belong to them. This is a Voronoi analysis of separation of space for the centers. This line here, this line here, this line here, this line here, right? And you see that basically all those points here will correctly cluster. There are some missing points here. On the edges. So it works, that a very simple procedure works relatively fine for this clustering. Basically, all the algorithms in clustering are variation of this thing, one way or another. And okay, variations of this is assigning, for example, weights to the distance in order to define if the value belongs actually to this one or to this one. And let me see. Okay, so this one shows a little bit like a video, the frames that the system is taking. We start with the original points. We decide 5 centroids randomly located, right? Next iteration, we compute the distance, we compute all the Voronoi and we decide, okay, this area should belong to this. All those that belong to this one, compute the centroid and move the centroid to this location. All those compute the centroid and will move the centroid to this location. All those here, this one already got it right here. So it will move the centroid from this location to this location. Here you get it. Here is pretty close to the actual center, this one. You move it slightly, all those points will belong to it. Probably after 3 iterations, not more than that, you get it. The clusters well identified. It's actually very beautiful algorithm. It's simple, it works fine. Well, let me see if I can do this. Yeah, imagine that you will start with this situation. What happens when one of those coalesce? This is why you never do this once. You will usually start with several trials, and that's why you can do this in parallel. I think they can parallelize that sort of operation. So imagine that you just select randomly, and you were so unlucky that you put just here one near here, another here, and those two here. When you compute this one, okay, this one probably will move a little bit, but it's already there. In this area, those two regions will compete for this point. So the centroid will be in the middle, weighted for the number of points that you have on each location, but will be somehow in the middle of that. And those points will probably coalesce here or become separated with a different point. So those points probably will go here and this will go here and will become the same. Or this one will move here and this one will be displaced to this side. So slightly different initial conditions will produce different results, and that's why you never should trust just one solution. Okay, here is the same k-means when you fix the number of clusters to 5, but you are asking for 10 different initial points. 10 different instances, they will propagate and they will see they produce the same result. Some of them will, some of them not, but most of them will produce a very similar result. They average and they return the solution. This one, I never use it. Okay, this one is an example when you were asking for 3 clusters instead of the 5 original, 8 clusters instead of the 5. The kind of solutions that this algorithm produces. this kind of thing I use very little. So there are some advanced things that I'm not familiar with. Okay, so probably much better than continue with the clustering is something that I rarely use. Much better will be giving you time from here to fall to explore the classification or regression, whatever you think that fits better for you or could be more interesting. You have the data sets that you can download in the input and start exploring all those concepts that we saw. I never use anything bigger than the traditional k-means for classification. They have more advanced things, but I never use them. So you have the time. For tomorrow, we will take in those two during the morning and introduce neural networks with, I will probably, for the networks, I will use PyTorch first. It's one that it basically extends NumPy. So if you are familiar with NumPy, PyTorch looks really nice because it's basically the same thing. Except for you are now able to put those matrices on GPUs and you can process them and you can operate with them. So it's like an extension of NumPy using GPUs. And the traditional one is TensorFlow and Keras. So I will split the time between those two for deep learning. We'll see. Okay. So take your time if you want to explore one classification or regression problem, and familiarize yourself with that. It's up to you.
I'll be using the regression, but I'm pretty sure that's how I installed up. I don't think there's way better ways to do that. I'll say terminal instructions. All right, let's take it. I'm going to speak to that. Do I have those?
I think he's all good. So.
Cameron, are you done?
Yes, to stop it.
Yeah.
We'll see you tomorrow.
Okay,
Tomorrow.
see you tomorrow. Pause or stop?
I think just stop, yeah. And then stop share after that.